recording start, we are recording.
And so is it going to show us here what layout we are?
We're
it's-
using this one.
Okay, the one
I
that's
already
green.
did-
Got it.
and
Yep,
you can
got
do
it.
by going preview.
Okay, got it.
Hey.
Okay.
So what I'm going to do is still,
Hey.
still recording start. I'm going to just take us to lighting control so they can't accidentally stop the recording.
Okay. Okay.
Thank you.
Guillaume, did you see, like, you can, I just want to show you.
Hey.
You can pick if you want.
Okay, you're changing the recording as you're doing
Oh, I'm
it.
sorry,
Yes,
sorry.
we're
I didn't
live.
know you put.
We're recording.
Oh, sorry. Okay. All right. So we know it's recording because the digital, why isn't it moving? Oh, it is moving.
Yeah.
Okay. So now we've got the view that is going to be, it's going to be the whole room,
So we do
right?
the recording preview. Currently, because there's no PowerPoint for this fellow, we're getting all three.
Yeah.
When someone is using PowerPoints, we will zoom in.
Yeah.
Did you guys have a
And
slightly
then we go
larger
into
chalk?
presentation.
You have to zoom before.
They're really tiny.
Otherwise you get on
Yeah, that's what you.
We'll be back.
And then you have to push presentation.
We'll be back.
really tiny.
Because he's going to be this till about an hour and 15 minutes.
Okay, thank you.
So don't sweat that, but let us get us back to the right way for this fella and zoom back.
There's some falling
I guess. Yeah.
There we go. We're there, and we're still recording. Nothing changed.
Oh yeah.
Tick tock, tick tocks. Recording is still stuck, but I'm just going to take us off this page so no one can accidentally bump that.
Thank you.
And take us to lighting control.
Okay, so now
Okay.
we can't
But we
answer.
don't know what happened last time.
No.
Okay. All right.
The only thing I can
Quick question for you. Yeah, Chuck, because his little one.
Yeah.
Have they? It's because you said that we're so organized. I know we have to touch.
Yeah, I think there's some little pieces I can try to manage,
I can try to get some.
but if you
I
find
know
a
it's
bigger
because
one,
you said that to me.
there's some little pieces here that I think I could try to survive. A slightly larger one. Yeah, it's good. Yeah. Check. It's not on? I think I turned it on.
Is it? Is it a little green light? I see a little green light.
Little green light.
All right, why aren't you?
Done. Hello.
It's just real, the sensitivity is really low.
Maybe it needs more volume or.
Well, hold on a second. No, not that.
More spicy than I saw.
Yeah, the chicken, right? Yeah, super spicy.
Yeah, you're coming
Yeah,
through.
got the same.
Say hi.
Hi.
Okay. I just increased the sensitivity for it.
Yeah, that's
Now,
awesome.
If there's a Q&A, we have a handheld that can be run.
perfect, yeah.
It sits right there for you. Clicker. Or you don't even need a clicker. You just hit chop. I can't. It's too low tech for us.
I know, guys.
We are
No, it's
currently
good.
recording. We cut all this out when we actually submit. So
It's cool.
you're good to go. What time do you wrap up?
3.
So that would be 2 minutes to 3, so we can reset the camera for the PowerPoint presenter after.
Sorry, Joe. I saw you coming. Yeah.
Thanks very much. You're the
We're
best.
recording and all set. We'll be back in about 10 minutes to 3.
Perfect. Thank you.
Where's Guillaume? Should we get? What do we do? Should we wait for Guillaume, or what happened to Guillaume? She brought me one, buddy. She brought me one. Yeah. Thank you, man.
I'm going to follow the color.
Ah, thank you. Okay, should we get started? Awesome. Well, having a lot of fun, so I hope I don't kill the party with my lecture. So what I'm going to be talking about today and tomorrow is goes under the name of statistical decision theory. So I'm going to tell you a little bit of a background story of where I picked this up and why I think it's fun. So many years ago, when I was an undergrad, I was an econ major. I'm originally from Mexico, so I was doing my undergrad in Mexico. And I took a bunch of different classes, a bunch of different econ classes, and also a bunch of different classes in applied math department. And some of the classes that I enjoyed the most were the classes in which kind of like after one or two lectures, you knew very clearly what was the object that you were studying. So I'm just going to give you an example. I walk into a general equilibrium lecture, and then someone defines an economy. You know, it's like, oh, what's an economy? And they say, like, well, you know, an economy is just a collection of preferences that represent consumers. It's like a production set. Like we can think of these just like what the firms can generate. And then they're interacted through something that we're going to call a market, that is some sort of price system. You know, given this price, consumers choose things. Given this price, firms produce things. And then the market just makes sure that everything clears. So I thought, well, you know, that's very easy to understand. Then there are a bunch of problems that arise of this, like what's a good equilibrium concept, how do you handle these things when there is uncertainty, and that's what makes for a semester-long course, you know. Similar experience when I was taking game theory. So you walk into the game theory class and someone gives you the definition of a game. You're like, at first, how are they going to define a game? They say, well, you know, they're players, and each of these players, at each point in the game, they have an information set. And in the information set, there are a bunch of actions that these players can take. And then there's a payoff that corresponds to what they do and what the other players do. So either they have complete information in the sense that they know all the aspects of the game, payoffs and preferences of the other players. So the only thing that they do not know is what they're going to do. Or they don't, in which case, you know, we have to think about how to model the fact that they don't know everything. But, so what we're going to try to do in the course was just figuring out just what's a good way of giving a prediction of how the players are going to play the game. So brilliant. So you go a semester going through all the different things they probably learn. What's a good equilibrium concept, equilibrium refinements, the problem of perfection, how things change when you move from static framework to the dynamic framework. So, and same if you ask me about like the math classes, right? You walk into a class and you're learning about topology, and someone comes to you and gives you a definition of what's a topological space. And then you spend the rest of the semester just looking at properties of these topological spaces and, you know, continuity, homeomorphism. Measure theory class, same thing. You walk into the room and then someone tells you, well, you know, this is a measurable space. And you spend like the whole semester just thinking about properties of, you know, either measurable functions or just probability measures and their properties and the things that you can define. Yeah? So I walked into an econometrics class, and to this day, I still am not sure what I was supposed to get out of it. Like, and then there are different versions, like depending who you did econometrics with, right? But some folks like to start with linear regression. And so I'm like, so what's that? I mean, what's the goal? And I remember back in the day, I think things might have changed because of the focus now on causality. But, you know, back when I was an undergrad, there was like, yeah, you know, we're going to discuss these three different things. We're going to talk first about identification, then we're going to talk about estimation, then we're going to talk about testing hypothesis, and then we're going to talk about inference. And it seems like, so what am I learning? It seems like I was just getting a bunch of recipes from a cookbook. So very hard for me to think about really what's the general problem that we're trying to solve? Like, you know, if someone asks me, what's econometrics, how would you define this? So, I mean, I don't know if you had a similar experience, like maybe this is just I have a very peculiar way of thinking about things, so I need to see definitions and stuff like that, and I just didn't get it when I was an undergrad. So I got into grad school, and I was very fortunate to get a class from Ulrich Müller. He's now at Princeton. He was visiting Harvard when I was doing my PhD, and he introduced me to this framework, statistical decision theory. Our advisor, Gary Chamberlain, was one of the persons that you know, kind of was also pushing the idea that it was in the benefit of graduate students to learn a little bit of this. And so what I'm going to talk about today is that statistical decision theory. So hopefully by the end of these 2 lectures, maybe 3 if I need to take a little bit more longer time, what I would like to, for you to know is what's a statistical decision problem. There's going to be a general definition of what's a statistical decision problem, and how a bunch of the things that we do can be just phrased within the language of, you know, what's a good decision rule for statistical decision problem. Okay, so I'm gonna do statistical decision theory, and so what I'm gonna try to give you is what is a statistical decision problem. Statistical decision problem. And then there's going to be this notion of decision rules. And kind of like the question that statistical decision theory is going to try to answer is what's a good decision rule? So there are going to be 2 general principles of finding good decision rules, and I'm going to be talking about them. So there's going to be the principle of finding good rules using the principle of prior posterior type of reasoning that I'm going to explain more clearly, and then I'm going to also talk briefly about this other principle, the minimax rules. And in between, I might, there are a couple of things that you'll see that are kind of like basic building blocks of the statistical decision theory framework. So one of the components of statistical decision problem is a statistical model. And so just going to give you a general definition of what a statistical model is. And in the context of statistical model, there are a couple of things that sometimes make the analysis of finding good rules simpler. It's the notion of identification. So I'm going to talk about statistical model and identification. And so then I'm going to try to give you a couple of examples just that show that a bunch of the things that you already know about estimation, hypothesis testing, construction of confidence intervals already falls inside this framework. But hopefully I'll give you a couple of other examples that are not straightforward applications of neither estimation, testing, or construction of confidence intervals that I think are still reasonable problems that economists could be interested in. So I'm going to describe briefly what it's called the treatment choice problem. You're going to see the presentation that I'll give later in the conference. I'm going to be also talking about a decision theory problem that arises in experimental design. But so my hope is I've been trying to sneak this material into the different courses that I've taught. So when I was at Columbia and I was teaching first year PhD econometrics, I would give first 1 or 2 weeks a couple of lectures on statistical decision theory. So now I'm teaching a second year course in topics that are at the intersection of econometrics and machine learning. But I start with these, and kind of like the pitch that I give to the students is like, if you buy at all into this notion of data-driven decision making, kind of like the intellectual foundation for thinking about what that means is this framework. And I think it should be very appealing to economists. So yeah, so I think we're going to have more fun if you ask me questions, if you interrupt me as I just present you the definitions. It's going to be really basic, so I think that the goal is that it's supposed to look basic because it's really kind of like easy and foundational. But yeah, really, I think by the end of today and tomorrow, you should, hopefully you're able to be in a better position than when I was an undergrad. So let me start. So questions, comments so far, reactions? Okay. Yeah. Or write bigger. Yes. Yeah. I'll do that. Okay. So so I'm gonna start doing. So the lecture is going to be a mix. So I'm gonna. So I gave you a general piece introduction. I didn't really define anything, but I'm gonna try to move between high-level things and more concrete definitions. Okay. So so just gonna break it in very simple terms. So decision theory, it's really how we make decisions. One of the definitions that I learned of economics as an undergrad was that economics was the science of decision making, or the science that studies decision making. So there's definitely going to be that aspect. So at some point I need to present to you a definition of, there has to be a decision maker that is trying to do something. Now, the reason why it's going to be statistical is because this decision maker is going to have access to data. So that's why this statistical decision theory. So the first block that I want to present is just like, well, if I'm really going to claim that I'm going to have a general formulation, such as the definitions that I gave you of a game as an economy that are pretty general, I need to start thinking about how I'm going to be thinking about data, right? I mean, in the abstract, how do we think about data? And how is it useful for decision making, okay? So that's where I'm gonna start. So the way this framework thinks about data is that the data that you see in the screen of your computers, whatever software you use, or even if you're still using spreadsheets and you open a spreadsheet and you see a bunch of things. So data in this framework is just going to be the realization of some random variable that lives in some space. There's also not going to be this arbitrary distinction that also happened in my undergrad, that there was like a course for cross-sectional econometrics, and then there was a course for time series econometrics, and then there's a course for time series data. And then, there's the spatial data and employer-employee match data and all these sort of things. So data, they're what they are. So, this framework, I think I like it because you don't have to think much about where it comes from. There are no dimensions. So I'm just going to say that, so make X be a random variable taking values in some set. Let me do calligraphic X as opposed to X. So realization of X, which we're going to denote it as little x, will be called data. And so under this definition of what data is, you really don't need to constrain yourself on, whether the data that you observed was, cross-sectional data, and this is IID from some distribution, or if it's time series data, and what you observe are t periods of time, or if this has more a panel structure, and therefore the space where it takes is more like a matrix, where you have a bunch of individuals that you observe over time, or it doesn't matter if it's a network. What I tell my students now in the machine learning class is that, well, this could be, for what we know, counts of words in documents, or it could be pixels that describe an images. It doesn't really matter. It's just what it is. And so the first real definition that I think for me was kind of like a very helpful thing to read about is the notion of a statistical model. And so the definition is going to be very simple. So a statistical model statistical model for the data is a collection of probability distributions so talking about here about probability distributions or probability functions, these are just really probability distributions defined over this space. I mean, if I were to do this more formal, this would be a measurable space with whatever set of events you want to attach in here. And the probability distribution or function would just be attaching probability to those events. That's kind of like what you learn now in inter-problem statistics. So that's one. What statistical model is going to have is it's a collection of them. So I have a bunch of them. And one trick that I'm going to use is because it's a collection, I kind of like need to have a way of creating an index over these so that I can call each one of them if I want to. And the way I'm going to do it is, so I'm going to invent just a little index that I'm going to refer to a parameter. And this parameter is just going to live in some space that I'm going to call parameter space. And this is very typical. You could call the indexes in whatever way you want. You can put whatever terminology you want to, but it's very common just to refer to whatever is keeping track of what's the element inside this collection as a parameter and set where it belongs, a parameter space. Okay, and just one quick thing is that there's no assumption here that the parameters that are indexing these distributions have to be a finite dimension. So even though I'm using parameter, I get this question all the time. Parameters that live here could be objects of infinite dimension, and this is therefore the most general definition that you can see of a statistical model. Does that make sense? Yep. Yeah.
At this point, do we need to say that the statistical model includes the probability distribution that X follows?
Not yet, because I haven't really haven't taken any stand on things like there's a true data generating process or anything like that. I'm just saying for a practical perspective, what's a model? And then there are a couple of definitions that I mean, I can actually be a good thing to add, but say, I'm not going to do it today, but a good follow-up for this definition could be saying that we say that a model is, say, correctly specified if there is one parameter theta such that when you call the distribution that corresponds to that parameter theta, that matches the true data generating process. So that would be correctly specified model, misspecified otherwise. I don't have to do it right now because, again, and this is one of the things that I want to convince you is that there's kind of like this almost frantic obsession for thinking about there's a true data generating process out there and I just want to figure out what is it? I just want to know. But I think there's a little bit more of a practical approach to the problem that says, well, I just have data and I want to use it in the best way I can to solve one particular action. That might involve estimating the true data generating process, but it need not to. Okay? So that's why I'm not going to have the explicit mention of misspecified and correctly specified models, but it's a great question. Yeah. And then so interestingly, yeah, I mean, I don't know how much of you guys see formally the definition of a model. It's come up when I was working at New York University. Interestingly, Tom Sargent stopped by my office one day and it's like, Pepe, if you're going to be teaching first year econometric, there are two things that I want the students to know about. One of them is that they can define a model. And I was like, perfect, Tom, because I have that in my slide. And then the other one was he wanted students to be able to know, to do base rule. So that I think is going to show up over here. So at least I made Tom happy. So questions about this? Perfect. And just in terms of terminology, I put this in the notes that I think were shared with you. I was tracking just other common terminology for statistical models. This part of the old theory of Lucy and Lecan that uses the term statistical experiment. So that's very common. Micro theorists are kind of like used to that terminology, so they use also statistical experiment. Sometimes they call these signals, but it's pretty much the same. It's fix something and you give me a distribution over the data that you see. So this notion of parametric and non-parametric, I already commented on it. I put a couple of references where you can see this in one page from people with more authority than myself. So, and then there are a couple of examples that probably it's worth mentioning, like maybe things that you've seen as a very common statistical model for real value data is a normal model. So the collection of distributions are going to be normal distributions that are indexed by a location parameter and a variance parameter. So as you collect all those distributions, that's just a scale, location, univariate normal model. Models can be more complicated. I mean, you can take it a notch above. Could be a regression. You have slope coefficients, and you have the distribution, joint distribution of residuals and covariates, and that gives you a full specification for the joint distribution of outcomes and covariates. So one question that I just thought about asking based on what Guillaume was talking in the morning is, so imagine that you see, so example, so imagine that you see data and you want to write and assume so Guillaume wrote something like this in the morning. And then where Q is the quantile function for quantile U. Yeah, so one question for you is, I mean, if you had to just describe to me what's the statistical model that is implied by this notation, what would you say? Is there a model here? I mean, to start with, is there a model, or does this fit into the definition? I mean, it seems like at least I have one of the ingredients because I have data. This is just like, a collection of outcomes and covariates for n individuals. And this is kind of like telling a story of how these things could have been generated. But just how do I close the circle? How do I write this as a model? What are the parameters of this model? Yeah.
Would it be the distribution of your x, so fx, as well as the quantile function q?
Excellent. So that gives you a statistical model in the sense that if you fix one of those elements in your collection, you fix one of these distributions and you fix one of these functions, then you now have a way of being able to generate this data, right? Does that make sense? So that's how I would think about what a statistical model is. I mean, this statistical model, you can see very clearly that it's a non-parametric model because I'm not imposing any restrictions so far on what this is. Right. Now, I was asking Guillaume about like what is the parameter space in this model. If I really were to ask you, it seems like, well, for this one it's easy because it's any possible marginal distribution on X. There's a constraint that I have to have IIDness between yi and xi. And then, well, the quantile functions, probably there are a couple of restrictions that I need to impose because I need some sort of, for a fixed X, I need monotonicity in the use, so that would need to enter my definition of the parameter space. Yep, does that make sense? Okay, excellent. Perfect. Okay, so that was.
Sorry.
Yeah, please.
When you're talking about data and we're giving us examples, these
Yeah.
are all examples that like we can see in our computer, like pixels or things that we have access to.
Right.
But you also mentioned earlier when you were thinking about causality and things like that.
Right.
I can imagine information like potential outcomes being something that are unobserved.
Absolutely.
And I've heard people call it, that's also part of your data, it's just unobserved data. And
Absolutely.
I'm wondering, do we make a distinction here about this data being observed or unobserved?
Yeah, here, what I call data, the only thing that I'm allowed to call data are things that I observe.
Okay.
Everything else is just something different. But you know, I don't have this in the notes, but this is what I give as a problem set in the example. So I think about the potential outcome framework. So there's a binary treatment. So you get intervention or not, and there's the potential outcomes. You get one outcome if you get treated, you get another outcome if you're not treated. And so the data that the analyst or the econometrician gets to see is just one outcome variable, which is if you were treated, then you see the outcome under treatment. If you were not treated, you see the outcome under control, and you see the treatment assignment. So the data is very clear. I just see one outcome and the treatment assignment. But so, what's a model in that case? Well, what you can think about a model as something that is parameterizing the joint distribution of potential outcomes and treatment assignment. Right? And why is that? Why am I calling that a model? Well, because if you fix that one, then you can just work out what's the distribution over the things that you actually see. Right? Same when there are latent variables. If you have latent variables, that's not part of your data because you don't see it. But if you put a distributional assumption over that, that would be part of a specification of a model for the data that you see. Does that make sense? That's an excellent question. Thanks. Okay. So I did that one. So let me give you another definition that I think it's fun to just write. At least it was, it was just fun for me to see it. And I do a bunch of work on things that have to do with partial identification. So it's good to define what identification means. So I'm just going to put it because it's a property that only requires you to know what a statistical model is. So it's identification. And so I'm starting with a statistical model, and I'm going to say that the parameters in the model are said to be identified if for any theta prime in the parameter space we have that whenever these things are different, this implies that the corresponding probability distributions are different. So it's a very typical definition of statistical identification. So you take a model, You take two different elements in the parameter space, and if these two different elements induce different distributions over the data that you observe, then you say that the model is identified. Otherwise, it is not. Yeah, here it's just as long as there are two. Here, this definition asks you for any two, right? So this one is, you take any pair that is different, this gives you different distributions. So this is what you need to check for identification. For violations of identification, it suffices to exhibit a pair for which this is violated. Yeah.
It's more of the use of the language. Do we say the models are identified or the parameters as you?
Excellent question. So here, I'm making reference to the parameters in the model, but you can also say that just the model is identified. But if you say that the model, you just have to keep in mind that the definition of identification makes explicit reference to the parameter space.
Because models are always used by the term or associated.
Through the definition. Yeah, well, great question. Yeah. Okay, cool. Does this make sense so far? Okay, awesome. So let me then try another thing. Okay, so I have this basic concept of statistical model. So now I kind of like took care of the statistical part of decision theory, but now I need to get into the decision theory part, okay? So, so the way this is going to work is very simple. So let me just tell you in words what I'm going to try to do. So I'm going to be thinking about decision making under uncertainty. That's what the data is going to be useful for. And the idea is that I think a convenient way to think about this is maybe connecting to the idea of a game. Imagine that you're playing a game against me. There's a statistical model that is common knowledge between the two of us. So we have agreement of what the model is, so I'm not trying to trick you with that. So it's over the table, we know what a statistical model is. So now what I'm going to do is I'm going to take one of the elements in the statistical model, so that's one probability distribution, and I'm going to use that distribution to generate data. So that means that at random, I'm going to generate a value of x. So you're going to be able to see what the value of x is, but not the parameter that I picked to generate. Okay? So then you are going to have an abstract set of actions. So these are things that you can do or you're interested in doing. And I'm going to give you examples that show that this is going to be, you can take too many different forms. But the key point is that the payoff of each particular action that you can take is going to depend on the parameter that I picked that you don't get to see. Okay? So the way I'm going to be thinking about it is the following. So I'm going to start by saying that so there's a decision maker. That's you guys. So a decision maker has to choose an action A out of a set calligraphic A. Okay, so little a, I'm going to be calling this an action, and calligraphic A, just going to refer to this as the action space. I'm going to give you examples just to show that this takes a bunch of different forms. Okay? Now, to model the fact that the decision maker has uncertainty on the payoff that corresponds to this action, I'm going to give the decision maker state contingent payoff. Right, so we model the payoff of each action A using a, let me call this a state contingent payoff. And so there are two common ways of specifying this notion of state contingent payoff. You can do it by specifying some sort of utility function in the way that we typically do. So this would be a mapping that takes as inputs, say, the actions, and depends also on what is the parameter that I picked, and it maps back to some idea of real value rewards. An equivalent way of doing these things is instead of putting over the table a utility function, you can think of this as being a loss function. You think about this, loss function is the same. It's a mapping from actions and parameters to also the real line. And the only difference is the interpretation, right? Like if I fix a parameter theta, I prefer action A to A prime if the utility of A is larger than the utility of A prime. If I start with a loss, I prefer action A to A prime if the loss of A for fixed theta is smaller than the loss of A prime. Right, but this is just terminology. The point is that there is a payoff function. You have a way of, if you knew what parameter I picked, there would be no problem on your perspective. You knew exactly what action you would need to take, and then there would be no need to worry about doing anything. But the problem is that we do not know or you guys do not know what parameter I put in, what parameter I used to generate the data. So I think with this just quick preamble, I can define what a statistical decision problem is. I'll put this statistical decision problem. And I'm going to say that statistical decision problem is a tuple containing, so there's going to be a parameter space, statistical model, an action space, and some payoff function. And then, yeah, and so this was the definition that I was looking for when I was an undergrad, but it took me a little bit more time to find it. But yeah, pretty much this is all of my research. All of my research looks like that. So it was useful for me. Not sure if it will be useful for you, but questions about this right now? Yeah, over there.
So when you were setting up the game of
Yeah.
you choosing a parameter to generate the data that we don't know about that parameter, but we can see the data that's been realized.
Yeah.
At that point in setting up the game, do we now say that we are in a world with correct specification? That is, I, as the second player, know that the data the data distribution you used is parameterized according to cap data.
Absolutely. In this particular case, we're totally in the correct specification case because I constrained myself to generating these data according to one of the elements in the model. In the notes, I use a little bit of different language, and this is used also in some of the general presentations of this problem, especially the ones given by econometricians. So you can think that the payoff that you have, instead of being indexed by the parameter, is indexed by an arbitrary state of nature. So state of natures and the parameters of the model, they could be different. So for example, the state of nature could be the true data generating process and whatever space that lives on. And the parameter in the statistical model can still be whatever. Okay, so I'm going to be working on today under this assumption that I'm correctly specified, but that's a limitation that I have for today's lecture. It's not a limitation of the framework. Some of the reference that I have, especially some of the work of Chuck Mansky, that he takes care of that. In that case, there's still a little bit that, so when you're defining these, the econometrician, typically in these cases, you know you're misspecified in the sense that you know that the true data generating process do not need to be contained in your statistical model. But all you know about the true data generating process is like some general process, like, well, maybe the data that I generated was IID, finite mean, and finite variance, and that's it. It's a larger model. But you decide to operate with that more specific restriction that I call P of theta. That makes sense? Yeah.
So you've written that first is used to be well specified?
I'm here assuming that I'm well specified in the following sense, that whatever is payoff relevant for the decision maker is really tied to the parameters. So, and the way I explained the game, I definitely constrained myself to the fact that I was picking a distribution for the data out of the statistical model. Okay. So that by definition means I'm correctly specified.
In simple estimation, the U could be like the simple average of the loss function? Or?
Not quite, because if you see the dependence, so I'm going to get back to this, but here I precluded dependence from data.
It cannot even be an L in a fixed way. It's not there.
No, it's not there. It's not there.
Okay.
Can I give you a couple of examples? Yeah.
Is considered as the fixed algorithm because I saw from the population level, so uncertainty is coming from a parameter space, which is a
Yep.
state space. So the question is like the theta here is considered as fixed or random.
It's fixed. It's no randomness in this. It's just theta is just something that indexes the model.
So it's fixed.
Yeah.
But if we consider the average performance of theta, so we kind of like put
The average what?
average performance of the theta.
Absolutely, you can put a prior, but then that'd be your choice. It's not the modeling choice. It's your choice.
Then theta is the random.
You make it random. I didn't make it random. You're making it random, and that's totally fine. That's going to be connecting to those ideas when we look at this base principle and the minimax principle. But in the framework there, I didn't put any restriction on this being random. I didn't say theta is a random variable.
So here, how to understand uncertainty here before looking at the data. So there's uncertainty here because like the parameter space, we don't know which one is the true parameter.
Yeah, you don't know which one.
There's uncertainty here before we looking at the data.
Yeah.
Single data.
Yeah.
So we have a randomness here.
So is the only way of modeling uncertainty over a set of objects is being Bayesian? So you always follow Savage's axioms. You never violate the independence axiom, for example. You don't believe in Elver's paradox? Yeah, modeling uncertainty or just trying to capture the uncertainty, putting a prior over this is one way of doing it. Another way could be just you put a bunch of priors. But there are other ways of doing it. So that's why right now it's just a description of what indexes your payoff. Does that make sense? Yeah. And you had a question as well.
So it was sold for,
Yeah,
for
okay.
the first comment.
Okay,
Yes,
okay,
thank
okay.
you.
Yeah.
I'm trying to understand where data come into play in this problem.
Yeah.
Because, so if there's a, you're probably going to get into this tomorrow or something. But
Yeah, in a couple of minutes, I think it's the next definition that I have.
right, so if there's a subsequent arrival of data, then this action is meaningful, right? Because right now I don't see how this is different from us
This is just a definition of a decision problem. I haven't told you exactly what's going to be the decision maker trying to do.
Okay, because you mentioned this a little bit earlier. If I know the parameter, then the action is obvious, right?
Yeah, absolutely.
So that dimension of the action is sort of, I guess if I can guess what the parameter is, if I have a really good estimation, which you haven't talked about,
Yeah,
then that action becomes.
absolutely. You're totally right. But that's just because I think you're one step ahead of what I'm going to try to define now. Right, so I mean, if you think about in the quick description that I just gave you on, I pick the parameter, you get to see data, but not the parameter. So I'm going to adjust a quick definition. And I'm going to call this decision rule. So I think as it was suggested here, I told you that if you knew what the parameter is, then you don't need to really worry about what's the best way of using data to pick the right action. But the reason why this is statistical is because the focus is going to be on you observe the data before taking an action. So you now opened up the possibility of using the data to condition your actions. So I'm going to define a decision rule as a function that maps data to actions. So a decision rule is a mapping of measurable mapping D from the set of possible data realizations to actions. I know that the only thing that is happening here is that, using a little bit the jargon of game theory, is that I'm going to be thinking about a case in which I really want to ask the decision maker to operate under commitment, in the sense that what I'm asking for this person is just not to tell me what you're doing now with the data that you have. I want you to rationalize it in the sense of, well, you can do whatever you want with your data now, but just explain to me what is the thing that you would do if you were to observe or obtain a different data set. That makes sense? So the commitment, it's through the definition of decision rule. And you're always free to ignore the data that would be captured by this, because you can always, pick a rule that, regardless of the data that you see, picks up an action that maybe you think is the action that is correct under whatever beliefs you have about the parameter space. But so the role of the data is here, and the big question in statistical decision theory is, if I'm facing a statistical decision problem, what's a good way of picking a decision rule? That's it. Does that make sense? Questions? It's clear? Okay, so now let's get into, so I want to get into the subject of what's a reasonable decision rule. And so far this is a pretty general framework, so what I want to give you is a couple of examples that are just special cases of this model. So here are a couple of things. So I'm going to give you two that are really, really common examples and that you've seen probably a bunch of times. Then I'm going to give you two others that are slightly different. They kind of look like estimation or testing, but they're slightly different. So first I'm going to do the typical ones, okay? So I'm going to do so I'm going to describe an estimation problem, but I want to describe an estimation problem in this terminology, where I just give you a model, an action space, and a payoff function. Okay. So here's a general description of the estimation problem. So I start with an abstract model. So this need not be parametric. So the elements in the parameter space can be of finite or infinite dimension. So in this game that we are playing, the action space that I'm going to give the decision maker is one in which the only thing that you can communicate back to me or communicate back to the rest in this game is an element of the parameter space as well. So meaning that in an estimation problem, the action space is the same as the parameter space in the model. So meaning the statistical model was common knowledge, and I generated data for you. You didn't see what's the theta that generated the data. And what I'm asking for you guys to think about is what would be a reasonable guess of whatever generated the data. So the way to just characterize that is just saying that in this decision problem, the decision maker is constrained to have an action space that matches the parameter space. So here's an example of loss function for this problem. For example, so now let me assume that theta is an object of finite dimension, just to make it slightly easier, but need not be. I can take something like and so again, with this idea that if I knew theta, then I would want to report that value as my best action. So that would be what you would do, because that's what minimizes the loss. In general, for all the actions, I get unhappy whenever I'm far away from the true value of theta, right? So that's in the case in which theta is a vector, but if you extend the notion of norm to the case in which theta is, say, a function, similar logic applies, right? Perfect. And so decision rules in this case are just mappings from the data back to the parameter space. And decision rules in estimation problems are typically called estimators. And this is a general description of what estimation is. Okay, so let me give you another quick example. Yeah.
Not relevant, but just because. So you decide into theta or into big A?
Yeah, you decide there.
Oh yeah, okay, here it doesn't matter because they're the same. But
They're the same.
Yeah.
Yeah.
Okay. But good, like emotionally, I'm picking my action.
Could be different than the parameter space in more general problems. So I think on Wednesday, I'll give you an example of a prediction problem. I mean, this is the type of problems that arise all the time in machine learning.
Yeah.
So you can think that the parameter is really the joint distribution of y and x, whatever that is. But say the action space in that case are functions that map covariate values into whatever space the outcome variable lives.
Okay,
So they're disconnected.
And I guess the question does have some sense, because you could have an estimation problem where A is not equal to theta, and then it seems like I really want a story where my decision takes me from chi to A.
Yeah. Yeah. And that's the general definition of a decision rule. Yeah. So this was just one example. Okay. Awesome. So let me give you another example. So it's hypothesis testing. So I start again with the same thing. Right, so there's statistical model. So now I'm going to add a little bit extra of notation here. The parameter space is just a set, right? So I'm going to partition the parameter space. So partition means that I'm going to find two sets that are disjoint and that have the property that when I take the union, they give me back the parameter space, right? Okay, so let me call this theta naught and theta 1, partition theta. Right, meaning the union of these gives me this, intersection is empty. And so now here's the problem. So same thing that we did before. So I generated the data, you get to see the data, but not the parameter that I picked. But now I'm not really interested in asking you to guess what's the parameter that I picked. What I just want you to do is that we start with a partition. And this is, again, common knowledge between the two. And I just want you guys to tell me whether you think that the parameter that I picked lives in this set or in this one. So it's a binary action problem. So I'm going to pretend that, say, the action space is, you can think of this as having two actions. Just for simplicity, I'm going to index them as action 1 and action 0. Right, say, just if you tell me that action 1, that means that you think that the parameter lives in here. If you tell me action 0, you think that the parameter lives in here. And I'm going to give you just an idea of a payoff function that is commonly used here. So it's the typical 0-1 loss. So now, for instance, one way of thinking about this is that if you tell me that the action is, the parameter lives here, but the true parameter actually lives here, you're unhappy and you incur a loss. So say, I can model this as saying this, but then if you tell me that the thing lives in here and it actually lives in there, I'm going to make this 0. Right? And then I can do the reverse thing. It's so this is for all the thetas in theta 0. And then I can do the symmetric thing for thetas in theta 1. So at the end, what I'm trying to do is, so imagine that I have actions over here, and I have parameters over here. One of them are in theta 0, and one of them are in theta 1. Right, and essentially, there are a couple of places when you are, you're okay. You don't feel that you incurred any harm, but then there are other places where you incur a loss. And then there are, of course, generalizations of these things, so that these payoffs, they need not be symmetric across this diagonal or symmetric across this diagonal. It's just one particular representation of these things. So, and in this particular instance, the decision rules are maps from the data to action space. So and these things are called a hypothesis test or statistical test.
Is these the type 1 and type 2 errors?
For example, I'm going to get to that in a second because right now the specification of the loss, I'm just giving you a payoff. But the meaning that we attach to type 1 and type 2 error, there's an element, a probabilistic element, right? It's how frequently would you be making the wrong decision depending on what generated the data. So there's one layer, and that would be one extra definition that I need to move from the specification of the laws to stuff that we talk about is like here, you know. We use this idea of a mean squared error or mean squared error all the time. The loss is going to be tied to that, but I need to do one extra thing because something needs to be integrated over. And same in here. I know just haven't introduced that part yet, but does it make sense? And then there's only one caveat in this literature is that, I mean, well, maybe here you see this more, but in the same way that in gains, there's a distinction between, say, a randomized strategy and a non-randomized strategy. Sometimes it's convenient to allow the decision maker to consider not only you know, a discrete action set, but all the possible distributions over that space. So in this case, it would be just the interval 0, 1. So this is a non-randomized test. If you put the whole 0, 1 interval, that would be a randomized test. But you know, that's the general definition of what's a statistical test. Okay. So then let me give you a couple more examples. Okay, so these ones are, as I said, conventional, very standard. Let me give you another one that I think it's like an interesting way of thinking about this problem. It's I think in the literature this shows up as a policy choice or a treatment choice problem. And so in these two setups, I was kind of like very general about what the statistical model is. Like, you know, this can be whatever. Like there's really, and again, for hypothesis testing, it's both parametric and non-parametric hypothesis testing. Everything looks like this. So I'm going to give you a policy choice treatment problem, but I'm going to give you a very parametric version of it just to maybe show you something that is slightly different, but that you can still connect a little bit in an easy and concrete way. So the problem is going to be the following now. I want to think about a case in which there's a policymaker that is making a choice between implementing a new policy or preserving the status quo. And I want to think about this policymaker as having a payoff function that depends on the true effect of the intervention, right? So it's not super straightforward to think about what's the right payoff here, but one particular payoff could be saying that this decision maker, if he implements, he just gets a payoff that is proportional to the true effect of the policy. And let me just normalize the payoff of the status quo to be 0 in the sense that it's relative to what it's in place right now. So if you preserve the status quo, you get 0. Okay, so where is data going to come from, or where is the data going to be generated? So this guy went to grad school probably in your generation, so he's really into randomized controlled trials. So the way he thinks is the right way to go to generate useful data for making that decision is run an experiment. So you run an experiment, and what you get out of the experiment is an estimated effect of the treatment, or the estimated effect of the policy. What would happen if you put the policy in place? So now, let me make an assumption about what this thing is going to look like. So if you allow me to call theta hat to be the estimated average treatment effect, and this is what you have in mind, is either if you don't have covariates, it's really the difference in average outcomes between treatment and control, or if you have covariates and you do some form of regression adjustment, it's just like the effect on the dummy variable that tells you whether you're in treatment or control. And whatever fancier version it is, if you're into the double machine learning thing or whatever, this is just what you would estimate out of the partially linear model with the double machine learning step. So, but whatever thing you have in mind, I'm going to be thinking about a case in which, because the experiment that you run is presumably large, it's not a crazy idea to think that the estimated effect is a normal random variable that is centered around the true effect, which is unknown, with some variance. And just again, to make it really simple, let me assume that this guy is known, so that the only parameter that I have in this model is really the treatment effect. So that's the part of information that I'm missing. So this satisfies the definition of statistical model, thinking that I'm assuming that the only data that you get actually is whatever estimated treatment effect. This is not the case for the person that is conducting the randomized experiment, because you observe more things, right? You observe the assignment to treatment control, you observe the outcomes in treatment and control groups. I'm thinking more about the perspective of really a policymaker that is really sitting in the office and just reading the papers that you guys write, right? So you might only get a table where you see, well, the estimated effect was this one. That's an estimator because it's not the true effect. And I'm going to take the variance that is reported in the paper as if it's were the true variance. So the uncertainty is just coming from the fact that I do not know nothing. Okay, so the action space is, again, I'm going to make it a binary action space. And what it's going to try to capture now is that if I pick action 1, that means that I'm implementing the policy at scale. If I pick action 0, then I'm preserving the statu quo. Okay? And so here's one particular loss function for this problem. I'm going to be thinking that, for instance, so if I decide to implement the policy, I get whatever the treatment effect is, the true treatment effect. And if I decide to stick to the statu quo, I just get right. And then there are variations of this. And in the notes, I just put something that is a slight variation of this, where this might be the per unit effect. So you might need to multiply this by the number of people that are going to be actually affected by the policy. And there could be a cost of implementing the policy that you only pay if the policy is implemented. So that all could be captured in theta, so it's no problem. And cool, and so here decision rules are again, they look like the decision rules that we had in the testing problem, because there's going to be mappings from the value of the estimated treatment effect to a policy decision. I'm sorry, I'm going to put this one again. Right, and in this case, you can just, like the literature sometimes refers to this subject as a policy rule. It's like, given the estimated effect of the treatment effect, would you scale up the implementation or not? Yeah.
Two clarification questions.
Yeah.
So here, a statistical model,
Yeah.
in the notation there,
Yeah.
it's just, it's a set of all normal distributions with variance sigma squared, and the way
Yeah.
you parameterize it is by whatever its mean is. Is that
Yeah.
okay?
Yeah.
And then the second question I wanted to ask is, I don't think we've, maybe we'll do it in a sec, but
Yeah.
made a relationship between D and U, and kind of what I imagine it looking like is we want to choose the D that maximizes
Absolutely.
the U.
Yeah.
Do we also
And that's just because that's what's coming next, right? It's like, once that I know what I want to do, how do I use that specification of U to pick a decision rule that somehow works? But right now, I'm only giving you examples of the first part of the framework, and what would be a particular payoff function, and what would be the notion of a decision rule. But yeah, the key question in statistical decision theory is how does that U disciplines your choice of action?
let me know
Yeah.
if this question is better suited to later.
Yeah.
But I'm wondering if, say that
Absolutely.
a budget and they have to
Yeah.
satisfy that budget.
Yeah, yeah, yeah.
That, do we have a notation set up yet to describe the set of decision rules that we can consider?
We can add this one. So the way I define this is like an arbitrary mapping that maps the data to the action space. When I start talking about the solution concepts, I'm going to place a specific notation for where the decision rules lead. If it's any function, I'm unconstrained. But if I have a specific type of functions that I want to put in, I'll be constrained. And just be the set, when you write the optimization problem that defines what's a good U, what's a good D, that's going to show up. But yeah, great question. Okay, so we are pretty good to here. So let me then just start with this notion of what's a good decision function, and then we'll continue next class. So we have 10 minutes, right? Almost 10 and change. 15, yeah. Okay. So then, here's a question. So. Okay, so then the question that we're interested is, in this framework is supposed to be a normative framework, pretty much in the same way that we think about game theory. You write a game, and you have a solution concept, and you expect that solution concept to give you something about how the different players are expected to behave. So we want to think about something similar in here. We wrote all the specifications that are relevant for thinking about what are the ingredients or what are the things that the decision maker would like to do. And so we capture that through the payoff function. But now the question is, how do I use the data to I really make sure that I'm making the best possible choice of action, right? Okay, so then first I'm going to try to tell you why this thing is a little bit complicated and needs kind of like this special notation. So first, I'm going to be working with utility function, and note that this object that I wrote here, it's always well defined, because so U is the mapping that takes actions and parameters to rewards or just levels of payoff. Theta is just a parameter. D of x, because it's a decision rule, takes as input data and outputs some action. And because the utility or the payoff function depends on actions and parameters, that object that I wrote in there is well defined. So now the problem is that the data, according to the statistical model, is a random variable, right? So that makes this payoff a random variable itself. So somehow you need to take into account the fact that even if you had some sort of knowledge of what's the true state of the world, and you decide to use one of these decision rules, the payoff that you would get from the ex ante perspective is a random variable. Right, and that's just like, that's what happens when we're doing estimation. I mean, for the particular, or testing, for the particular data that you have at hand, the estimator takes one value, but every time we take about or talk about things like what's the limiting distribution, what we're thinking is like, well, if I had seen this problem a bunch of different times, what would this estimator have looked like, right? So it's the same question here, it's just that the center is now in the payoff function, because that's the thing that is relevant. So one thing that I'm going to define is the following. So I'm going to fix the true parameter that generated the data, whatever that is. It's unknown, but I can just fix it because I have a model. And I'm going to compute, so I'm going to make this capital X for a second just to make it explicit that I'm averaging over this value. And here I'm going to say that I'm going to be computing the expected utility for a particular true parameter that generated this data. Okay, so suspected utility, if I do the same thing with loss, we'll just need to replace U by L. But it's on average, if nature had picked, or if I had picked this parameter theta for you, and you were to see this data over and over, if you fix the decision rule, what would be the average payoff that you would get? Right? And so this one, it's expected utility, right? So I'm going to just say that this is going to define a mapping that now depends on the decision rules and the true parameter, right? Yep.
So if we were to change what that true parameter is, just to confirm, it's changing both the evaluation of U and
Absolutely.
the expectation with respect to
It's this one over here and this one over here.
we're changing both of them.
Absolutely. And because I'm defining this as a function, that's totally allowed. You can fix a d and move over different values of theta. You can fix a theta and move over different values of d. Now, I'm calling this expected utility because I'm doing utility. Had I used a language of loss function, I could call this expected loss, and that's the typical jargon in the literature, a risk function. Okay? Risk or expected utility here, the key is that there are two arguments in it. It's the decision rule and the point in the parameter space. This means that the performance of different decision rules, or the performance of a particular decision rule, is going to depend on what is the parameter that generated the data, right? Yep.
So just going back to the hypothesis
Yeah.
testing example, it's kind of interesting because I feel like the way you usually think about hypothesis testing doesn't really fit into this expected utility framework, and it's like my preferences over tests is first I want to control the type 1 error rate, and then I want to maximize power. It's kind of lexicographic in that way.
Yeah.
And so it doesn't really feel like it's an expected utility. So I'm just curious, like,
Not quite.
is all of statistical decision theory kind of only looking at expected utility, or could I kind of just define some other objective function within this framework that might capture that type of preferences?
Let me actually, so I'm going to claim that this thing that your lexicographic preferences can be accommodated in this framework. Just, again, just separate between two things. So there's separation, I think it's the same thing that happened before. You're already thinking about a way in which you want to pick D. Here I'm defining an object that simply is reporting the performance of any particular D as I move over the points in the parameter space. And so let me just do that, so say the example. So hypothesis testing, right? So didn't start out at hypothesis testing with a utility function. I have a loss, but I have a loss that depends on my binary actions and the parameters, right? So I said that in that case, a decision rule or a test is just a mapping from whatever data you have to whether you reject or not reject the null hypothesis, right? So this would be reject the null, and this is do not reject. Right, so, okay, so then let me think about this 0-1 loss that I'm using, right? So, okay, so let me write this thing. I'm going to compute this expectation first for parameter values that belong to the null hypothesis, okay? So I'm going to report the expected loss for a particular testing procedure that you have in mind, whatever that is. The parameter value theta, right? Okay, so let's try to work it out. So now I'm doing this for theta and theta null. theta naught? Okay, so let me just write this one down. So you're either going to reject or not reject the null, but you're in a case in which the true parameter that generated the data is actually in the null. So when you don't reject, this payoff function becomes 0, right? Because that's how I set up the payoff function. So then the only part that is relevant to your payoff is how frequently you're going to be rejecting when the null hypothesis is true, right? So that just follows my definition. So this is going to become, so this loss now is going to become 1 whenever this test is rejecting, right? And this is supposed to be an indicator function. So this is just the probability under this parameter theta that the test rejects. So that's the computation for theta in the null space, right? So now I'm going to do the same for theta in the alternative space. And what I'm going to get is 1 minus the probability of rejection, right? So this is the rate of type 1 error of the test, and the other thing is the rate of type 2 error of the test. So, I mean, you can have whatever preference you want over these rates of type 1, type 2 error, but the performance of the test for you or for any other people is going to be described in terms of these two components. Any test has a corresponding rate of type 1 error and a corresponding rate of type 2 error. Whatever preference you have is a separate business.
Yeah, I think I follow you. I guess what I'm saying is that I want to have preferences where if this is greater than 0.05, my utility is negative infinity.
But again, that goes to the place of how you choose or how you think about choosing a good decision function. This is only telling you that an ingredient that is going to be a component or an ingredient that is going to be taken into account to pick a good decision function is the performance of the test over the different values that the parameter can take in the parameter space. So that means that what this is saying is that whatever you have in mind that is a good test, it's going to need to somehow make a choice of how type 1 error is viewed relative to type 2 error. And then you can have, if you like 5%, then that's totally fine. But it's not excluded.
But so I guess I'm saying, how are you going to be able to do that if the L is inside of the expectation?
It doesn't matter, right? Because what I'm going to be optimizing is over these.
Yeah, I think I agree with Neil because your preferences are over the expected rejection probabilities.
You have preferences over type 1 and type 2 error profiles that this test induces. That's what the preferences are going to be. And so you have preferences that say, like, you know what, I don't even want to think about a test that has a rate of type 1 error larger than 5%. So within that class, you're still going to have to deal with the fact that within that class, you know, depending on what's the null hypothesis, you might have a rate of type 1 error that is exactly equal to 5% or below 5% if you have a null hypothesis that has more than 1 point. And then the power, you're going to have tests that, even if they satisfy that constraint, they're going to have different power at different points of the parameter space. Does that make sense?
Yeah, I think
So for every theta, you check these things, and you don't let the D's that give you excessive type 1
For example.
in the
For example.
key.
Yeah. Yeah.
Okay.
Yeah.
That's where the get kicked out.
Cool. So yeah, so essentially, the whole game in statistical decision theory is just going to be a couple of ingredients here. Let me mark this thing. Yeah, and I think this is the last thing that I mentioned, and then we're going to continue next class. But both in the hypothesis testing problem and in any other problem, I think what this procedure makes very explicit is that once that you committed yourself to have a statistical model, then it's not unreasonable to think that the performance of whatever procedure you have in mind is going to vary depending on what's the true data generating process, right? So you want to make sure that you are picking something that has good performance, for a bunch of values of theta. And there are two different ways of thinking about, two common ways of thinking about what good performance is. So let me write it here. So it's two general principles for choosing B. Okay, and so just before I mention these principles, so as I was telling you guys before, D, the way it was defined over there, is arbitrary decision rule. It's a mapping from data to the action space. For a bunch of these problems, I'm going to take the stand that let calligraphic D be the space of decision rules of interest right? And then I think you guys already gave two examples of this, because in the policy choice problem, if you have some sort of budget constraint or there's only a certain fraction of the population that can be treated, then that might change what the set of decision rules could be. For the testing problem, if you're really lexicographic and don't want to consider any test that has a rate of type 1 error larger than 5%, that restriction can be in here. It's just this is the set of all decision rules for which the rate of type 1 error everywhere in the null hypothesis is below 5%. So that's totally fine. That's your preferences. Just here it becomes part of the specification of the decision rules. But still, in most problems, there's still a bunch of tests, even if you're lexicographic. There are a bunch of different ways of coming up with a test that controls the rate of type 1 error. Many different ways, including flipping a coin and rejecting with 5% probability. So the two, let me erase this thing. So the two general principles are going to be I think I'm just going to mention them in words, and then we'll write the math. But so one of the ways in which we're going to be able to pick different procedures is, well, the payoff varies depending on where in the parameter space you're evaluating. So say I want to pick a rule that works well on average, where average now can be taken with respect to some distribution over the parameter space. And that's going to be the average performance criteria. But then there are maybe you're the type of person that doesn't really care about average performance, but you just really want to be protected about things going very badly in this parameter space. So you want to identify what's the point in the parameter space that gives you the worst performance, and you want to give a rule that performs or protects you against that worst case scenario. And that's called the worst case performance, or the minimax principle. And so next class, I'm just going to give you definitions. So for this one, there's a really easy way of thinking about how to generate rules via the average performance, just by applying base rule and the principle of posterior loss minimization. Now for this one, the worst case performance, it's a little bit more of an art to find the minimax procedure. But I'm going to give you a couple of examples of how these things can be solved, and one or two general results about that sometimes when you have procedures that minimize average performance, and if you happen to have constant risk over the parameter space, those things are going to be minimax. So I'm just going to discuss these, and also the notion that worst case can be done in terms of utility loss, or also in terms of something that is called regret. And those are the things that I'm going to be talking about next class. Cool? Awesome. Thank you. Yeah, awesome. Thanks for your questions. That was cool. Hey.
So here in the policy choice question, policy choice. So in this setup,
Yeah.
we just observe one observation.
The estimated treatment effect,
The,
yeah.
the
State height.
noisy estimate.
Noisy estimated.
Well, so what if like we are interested in heterogeneous treatment effects? So for example, each individual.
Yeah, that can be modeled. That can be modeled. Different ways of doing it.
This
There's different ways of doing it. Like the simplest case, think about that you have only binary covariate. So you have men and women. So now you can think that you have a theta hat for men and a theta hat for women. So the data that you see is just this vector.
So kind of like consider like mixture.
No, because so here, instead of doing the mixture, I'm actually thinking that just thinking if in the experiment you actually have these two covariates, and these were baseline covariates that were available before running the experiment. You could estimate the treatment effects for each group separately. So you don't have to mix them. You can keep them separate. So theta hat would be a vector that has two estimators, the estimated effect for women and the estimated effect for men.
Okay, so you are saying that we try to stratify the sample.
For example, that could be one case. That could be one case.
And then like each stratify has
All we have to do now.
Yeah, but then it depends, like the policy problem. What's the policy problem? In some cases, you might not be able to assign treatment conditioning on this covariate. It might be illegal to discriminate between men and women. But then in other cases, you could. So there's the thing: are you trying to figure out one policy for these two groups, having information about the two different payoffs, the two different estimators, or are you trying to do one by one policy, having the information separately for each group? This leads to different decision problems.
For example, like the two-stage experimental design. So in the first stage, we kind of learn this noisy
Estimator.
and for each certification.
Yeah.
And the second stage, we
Sorry. Give me 1 sec.
Magic box. Thank you.
Thank you, guys.
You're very welcome.
So it's kind of like the second stage, we want to, for example, like learn this.
It lives under here. Most of our microphones, not all of them. Some of them you'll find a bag of batteries instead because they die after
Just stick in here like that.
Yeah.
Is that right? That's charging?
Yeah. One of you in the T ring, the batteries that go into puck mics, put them in backwards. They weren't charging at all. They showed up to completely dead batteries and puck mics. It's nice. Okay.
You're very clean.
Dude, there's lights that come on when we do it right. Come on.
Throws against the wall.
So now we're waiting on.
say we have a interrogation of y on age and gender, or y on age square and gender. Then you look at example fit, and somehow solving the limiting problem.
Thank you very much.
Oh no, it's not that.
Now I'm working on paper that I'm working on Friday based on the work of the site selection problem that you guys by hand. We have a minimax regret solution for it, so we need to use priors. Yeah, I'm pretty excited. What do you think? I sent the page to you, Mike. Can you tell me what he said location? I don't know. Oh, okay.
And I bet.
So he's going to be your main advisor? Yeah. That's amazing. He's a master in decision theory. I should have said that.
Yeah, I want to get a story from
Hello. So I will be teaching now.
I'm sorry.
But I did not send slides.
Do you have a thumb drive? Do you have your
I
own
forgot
computer?
it. I have my computer, or I can log in on my email address and then whatever you prefer. Or is it easy to switch a computer?
It's easier to use this computer because it's already plugged in.
Okay.
So if you want to go somewhere and grab it and put it on the desktop, I'm gonna set you up because I can't be here at 3:30, so it'll be ready to go.
Okay, I do it quickly.
You just have to. Are you from University of Chicago?
No.
Okay, so what it's doing is it's defaulting right now, assuming you're at University of Chicago. You just want to go to, hold on a second. We may have to use a different browser if this is cached. It keeps doing that, so let us try.
Maybe as an anonym.
There's no one signed in here, which is the puzzling part. So, yeah, there's no one
Okay.
signed in.
Thing is, I saved on my phone, but I forgot.
I just want to see why it won't take us to Gmail directly, why it keeps redirecting
Okay,
us
but
to him.
this one is connected to the computer? No, because if I could connect my phone, it would be fine.
You need power?
Yeah, to connect to the computer. Because I saved on the phone and I forgot.
Oh, okay. There's no way I can connect this to this
Okay.
to this.
Okay, here I
There we
will
go.
do it.
I'm going to keep your email off the screen.
Yeah, but it's public. It's public, and if they don't see the password, it's fine. Oops. Yeah, I have it. Okay, so I will log out.
I can make assumptions that like say suppose the effect in Mexico is at most K or
Okay, so
Yeah.
let's just close this side here.
things that you're describing.
And then can't reach. And now let's plug this back in.
The right thing to do in Mexico is to not become the force. But in practice, you only use
Okay. There you go. And one thing I want to check here
Yeah.
is make sure that we are still recording. TikTok still recording, and at the view, wrong view. We need to put you. You're good to go.
Thank you very
All
much.
right. We're good to go. I'm going to let Diane know.
You can take the Diane and see you Team Christensen, people like to look at that. So maybe if you start looking into that, I think
how those categories are made in practice.
Ouais, je vais faire. En fait, ouais. Là, aujourd'hui, la moitié, c'est peut-être papier counterfactual distribution, c'est-à-dire comment tu vas décanter le conditionnel, un non conditionnel.
Ouais, mais je pense qu'il y a plein de gens qui ça va être la première fois qu'ils voient le concept. Fait que,
Ouais.
ça va être correct. Ça a bien été un vote.
Ouais, un vol direct. Non, non, ça a été très bien.
C'est top. Je pense que j'ai déjà pris ce vol-là. C'est Montréal-Zurich. Est-ce que j'ai Zurich?
Ouais, c'est exactement.
Ouais, c'est ça. Les prix, j'avais fait Seattle, Chicago, Dover, Chicago, Zurich.
Non, alors, ça s'est bien passé.
L'autre fois, j'ai fait San Francisco, Paris.
Ouais, ça c'est bon. Après, c'est toujours creux en train de venir. Enfin, il y a une journée de perdu.
Ouais, mais moi, comme venir ici, ça a comme fini par prendre une journée quand même, parce que il fait les douanes à Montréal, mais qui arrive 2-3 heures avant. Là, ici, je sais pas si c'est long pour toi, mais le taxi, ça a pris une heure et quart.
Bon, moi, j'ai pris les trucs en commun.
Ouais, la ligne bleue.
Ouais, la ligne, c'est bleu, oui, oui, ligne bleue. Et après, j'ai pris un train.
Ah, ok, le métro.
Ouais, voilà.
Ok, nice, ok,
Ça me semblait tellement loin pour prendre le taxi.
mais tu sais, c'est comme, quand je vais dans les villes aux États-Unis, souvent c'est 2 avions, minuscules, super derrière, avec un layover de 4 heures, à genre, je sais pas quel aéroport. Ça finit par être plus long qu'un entraînement à anyway. C'est juste le jet lag.
Ouais, ouais.
J'ai découvert les petites piles de mélatonine.
Ah ouais, ça marche?
Moi, ça marche très bien.
Ah ouais.
Les arrêts, comment ça?
Oh là. Normalement, c'est maintenant que ça va venir la limite, c'est la fin de ma journée, on est fini à 1h30. Mais comme je vais pas au dîner, là, je vais bien dormir, ça ira. T'as fini ça?
Ça va bien.
Ça va bien?
En fait, je travaille contre eux. C'était vraiment un genre musical. C'était vraiment un genre musical.
Ah ouais, d'accord.
Fait que, on va voir.
Mais pourquoi ils t'ont poussé à...
Donc, il y a des gens, il y a la moitié du département qui est politique qui pense qu'il va y avoir l'économie dans les sociétés, donnent leur propos de racisme, complètement débiles. Fait que, non, je pense que ça va même faire. Fait que ça c'est compliqué parce que c'est là pour la fête, puis très vite, c'est quelque chose un peu isolé, mais un an deux, je suis dans le bureau, je fais des R&R. Mais là, le problème, c'est qu'avec le moins, c'est pas beaucoup parce que c'est quand même un moins COVID. Fait que là, de devoir
Mais ici, t'aurais pu attendre.
Ouais. C'est déjà beau déjà. En plus, l'article que tu as vu au temps, je l'ai donné à
Ah oui, oui.
l'université.
Ouais.
Il est au journal, je prends avoir des nouvelles avant des grandes votes de l'église. Il y a un bruit qui s'est masqué et en train de payer. Fait que ça se trouve dans le vrai que c'est à l'automne, je ne peux pas vraiment l'envoyer. Si ça passe, on en fait 2 en 1 an. C'est comme, tu sais, moi, l'opération publique, c'est comme une parole académique, je sais pas
Mais c'est définitif? So, hi, hello everyone. Thanks, Guillaume, for organizing this summer school and for inviting me. I hope you are not too tired. So I will give 1 hour 30 today and 1 hour 30 tomorrow. Everything will be related to quantiles. I'm not so sure what optimization conscious econometrics mean. But I know what I do and what I like, and Guillaume invited me, so I will talk about what I like. And I'm pretty sure, I hope you will be interested, and hopefully you will be interested too. So I will just start by the question, why do we use quantile regression? Because we got an introduction this morning, and so just wanted quick historical, a little look at the history and why people are using quantile regression. Then I will give a few examples of the most common errors you can do in constructing quantile models, and which is, I can give a spoiler, which is to implicitly assume that the quantile operator is a linear operator. And I will give many examples of that. And one of them is the difference between conditional and unconditional quantile treatment effects. And because you can use quantile regression to estimate conditional quantile treatment effects, I will talk how you can estimate unconditional quantile treatment effects. We'll give usual results about estimation, algorithm, asymptotic distribution. And then we'll compare these two sorts of estimates. And to conclude, I will also compare with unconditional quantile regression, which is still a different method suggested by Firpo, Fortin, and Lemieux. Okay, so let's start. Historically, quantile regression has been introduced, invented, discovered, I don't know what is the right word, by Kanker and Bassett in a paper in Econometrica in 1978. And in this paper, and in the first papers, they have written in this period, let's say, end of the 70s, during 80s, actually the main reason to use quantile regression, the main reason they give to use quantile regression is the robustness. So they put that in the robust statistic literature, like people like Huber, Ampel, and actually they're assuming that the model is homogeneous in the sense that they're assuming that y is a linear function of x plus an independent error term, and we want to estimate this parameter. And we can do that with OLS, or with a trimmed least squares like Huber was suggesting, or using least absolute deviation, which is median regression. Okay? And they were comparing efficiency with outliers, things like that. But actually today, if people are using quantile regression, it's not for that, but it's to study the heterogeneity of the effects. And here, during the 90s, you have a paper, I'm sure that Guillaume mentioned it, by Gary Chamberlain, where he used quantile regression to study the effect of being member of a union on the distribution of wages. And he especially used quantile regression to show that the union will compress the income distribution. Okay? And to show that, you need to allow for the heterogeneity of the effect. Okay? And starting from that, then with his student Moshe Bushinsky, written a few influential papers in Econometrica in particular, then people have used quantile regression to study this heterogeneity, and I would say that today 95% of the application of quantile regression are to study this heterogeneity. So if you take the classic, so just the notation, introduce the notation. Here I separate the intercept and the regressors, and you will see why in a few seconds. So what is important is that we want to allow the coefficient, the return, like if this is characteristic, this will be the return on this characteristic. We allow it to be a function of tau. So we want to allow it to change with tau. While if you have what I call homogeneous regression model, where you have an error term which is independent of the regressor, then if you have such a model, which is also a classical linear regression model, where like epsilon is normally distributed and homoscedastic, then this model will imply that beta tau is constant as a function of tau. So if you just show generated data, if you have homogeneity, then all quantile regression lines will be parallel. Okay? So there is no reason to use quantile regression in some sense, because OLS will give the same slope. Only the intercept will change with the quantile index. Yeah, like I said, the only reason will be the robustness or efficiency. Because if you have fat tails, then median regression or another quantile regression may be more robust and may be more efficient, so will be more robust and may be more efficient than OLS. But it starts to be more interesting when you have something like here, the simplest case, the heteroscedasticity, where you see that the variance of y is increasing in x, and then the slope is changing with the quantile. Okay? And this is the sort of thing that we want to analyze with quantile regression. For instance, if what people typically do, they plot the slope as a function of the index. So you put the quantile index on the x variable, and you put the slope on the y variable as a y variable, and then you will see in such a case that the slope is increasing with the quantile, which means that if x increases, the variance increases. Okay? So actually, if you plot real data, if you put education or experience, you get something like that, and the wage, like a Mincer equation. You get something like that. And you have actually theoretical reason why it would be the case. Let's take experience, or let's age or experience. Then when you enter into the market, the firms has not much information about your ability. So the wage will be based on your CV, where you have studied and things like that, but different students coming from the same university, let's say, they will be very similar, and so the firms will not give very different wages. But with the years, the firms will learn about your productivity, your individual productivity, and so the dispersion will increase because of that. Okay. So you have model predicting that, and then you look at the data and you find that. So it's something that we definitively want to allow. Okay, so it was just his first point, and the goal was to explain what I call an homogeneous and heterogeneous model. The heterogeneity is heterogeneity in the slope beta tau as a function of tau. If it's flat, if it's constant, or if it changes with tau. Okay, so now let's come to the second point. It says the main mistake you can do when you try to modelize a quantile. So you want to modelize a quantile of y. And it is assuming that quantile operator is a linear operator. So I'm pretty sure Guillaume did that this morning. I could not attend. But in his book, it's what he's doing. And I am doing the same when I teach. It's very natural to do that, is to explain, well, you know OLS. With OLS, you estimate a conditional expected value of y given x. Now I will introduce a new method, it's quantile regression. We will estimate the conditional quantile of y given x. And then they look very similar. Okay? And it works well in the linear model, but there will be cases where actually it does not work so well. And then many of the mistakes that have been done in the literature are really to do something with quantile regression that we did with OLS, and it did not work. It does not work in all cases. And the reason is that the quantile operator is not a linear operator. What I mean is that if the quantile, so tau is a quantile index, number between 0 and 1, quantile of the sum is not the sum of the quantile. So it's completely, I mean, when you think about it, it's obvious, but it's easy to make the mistake. And this, of course, implies that there is no law of iterated quantile. So you can try, so if you try to find a relationship between the unconditional quantile and the conditional quantile, you can try the expected value, you can try a quantile, same index, different index. nothing will work. Okay? So there is not a function mapping the conditional tau quantile to the unconditional tau quantile. And the topic today is to see what we can do to map, and what we need actually is a full quantile function for all tau from 0 to 1, and then there is a mapping. You also need the description of x, but then there is a mapping from this conditional quantile to the unconditional quantile. Okay, this will be a main topic of today, but before we do that, let's see, okay, this is the first bullet point on this slide, but I want to give a few examples of things you can do. Yes, sorry, Guillaume.
Just for motivation, so the idea is we want the unconditional quantile, but we're starting with the conditional quantile for reasons of accuracy.
Okay, I will come in a few slides. It's if you have a treatment, then the thing is, I will be assuming conditional independence, so I need to condition X to make the treatment as good as possible exogenous, but then I am interested in the unconditional quantile treatment effect for ease of interpretation. So this will be the motivation. Okay, so first example, I will talk about it today. Second example is, so the first examples I will cover today and tomorrow. I mean, the third one, I will not have much time, but I will try to cover them. So the first one I will cover in details today. Second one will be double machine learning. You know, if you want to make inference after model selection, you have different methods. I will talk tomorrow about results by Chernotzukov and co-authors. For instance, you have double selection or double machine learning. If you apply this method in a naive way, it will not work. Like, you know, double selection is you regress y on x, and you also regress d on x, and then you use a union of the selected variable. Let's say you lasso, and use a union. If you do that with quantile regression, it will not work. And I will explain why tomorrow. It's related to the bias, which is weighted by a density. And so you have to weight with the density when you do these two regressions. Okay. So I will say more tomorrow, but it's a second example where if you do the naive thing that, I mean, if you do naively the thing that you are doing for the mean regression, we do for quantile regression, it does not work. Panel data, if you, with fixed effects, okay, if you first difference all y and x, then you will change the parameter that you are estimating. Okay? So you know with OLS, you can, let's say you have two time periods. You can first difference, or you can time demean, or you can estimate dummy variables. They are all numerically identical with two time periods. With more than two first differences and the fixed effect of the time demeaning, they give numerically different parameters, estimates, but they will converge to the same value. With quantile regression, there is no reason it's the case. First difference does not work because you get the quantiles of the changes, and which is not the parameter that most of the time you are interested in. And then explicitly estimating fixed effects, you have an incidental parameter bias, again, not a linear operator, which means that the fixed effect does not cancel. I mean. So I hope I will have time to say a few words about that. Then I've given other example, a very simple one, measurement error in y. You know that if you have measurement error in y and you estimate OLS, it's not a problem. I mean, if the measurement error is a classical measurement error, you just go into the error term and it's fine. With quantile regression, it's not fine. It will bias the result because you are adding noise to the depending variable, and so you don't know what is the original, the structural noise and the measurement error noise. They are mixed. There is a paper here, Hausmann, Liu, and Palmer in Econometrica, suggesting one solution. I'm not sure it's the end of the story, but it's a discussion of this point. Instrumental variables. Again, OLS, so mean regression, you can use a fitted value approach, like two-stage least squares. You can use a control variable approach. You can use a world estimator. They all give us numerically the same solution. Now, with quantile regression, if you naively apply two-stage least square and you do two-stage quantile regression, it will work only if the effects are homogeneous, like if beta tau is equal to beta. Some people have tried that. It does not work. I mean, you get results, this is the problem, but it does not estimate what you want to estimate. A naive control variable approach also does not work. A paper by Simon Lee, beginning of 2000, I don't remember which year, in Journal of Econometrics, implicitly somewhere hidden is the assumption that the effect is homogeneous. Okay? That makes no sense to estimate quantile regression. So here there are two solutions depending on where you want to impose assumptions. If you want to impose a monotonicity assumption, like Angrist-Imbens type of monotonicity assumption, then you can estimate quantile regression with an instrumental variable. It's a paper in 2002 in Econometrica. If instead you want to impose a restriction on the outcome equation, which is a rank similarity assumption, then you have Chernow-Zucker-Franzen. These are consistent. The first naive two are not. Control variable approach also, if you want to do it for sample selection, it will not work like Heckman style sample selection. You estimate inverse Mills ratio, then you have a non-parametric or semi-parametric version of it by Whitney and Huey, where you have a series. You have a series in the inverse Mills ratio to control for the sample selection bias. If you do the same for quantile regression, it will work only if the effect is homogeneous. Actually, it's what Moshe Bushinsky has proposed in a paper, Journal of Applied Econometrics, 98. He got the prize for the best paper in the last 2 years. And actually, the paper is wrong. Because he's assuming that the error term is independent of x, but then later in the application, he got different coefficients across quantile, and he interprets these differences and he said they are significant. By showing that the difference between that beta as a function of tau is not constant, is showing that the model is not valid. So you cannot do that. And if you want to find a solution, there is one in Arellano and Bonhomme, where they need to impose additional assumption. What they do, they restrict the copula between the error term in the selection and outcome equation. Okay? So they assume it coming from a known family, and then you can estimate the parameter of this copula. So this one is consistent, the previous one is not. With difference in differences, it's a little bit more, so less clear, but I think a naive quantile difference in differences is not attractive. Okay? So it's discussed in a very nice paper by Atten Niemans. If you don't know it, you should definitely read it. They suggest another model they call the changes in changes. And compared to the changes in changes, doing naive quantile difference in differences, which means that you take the diff equation, but you estimate with quantile regression instead of OLS. I mean, in principle, it's possible that it's a model that is not necessarily self-contradictory, but it assumes additive separability of the time effect, which is very unnatural for quantile models. And it's not equivalent with respect to strictly monotone transformation. What is meant here is that if you do diff in level, and then diff in log, you may get like positive effect in level and negative in log. It's possible with mean regression, and it's possible with this quantile difference in differences. And one of the big arguments in favor of quantiles is that there are equivalents with respect to strictly monotone transformation. So, yeah, it's the last square point here, is that they have good things. Okay? There is one difficult thing, which is it's not linear, but they have good things. And one of them is that they are equivalent with respect to strictly monotone transformation. What is meant is if you take the quantile of the log or the log of the quantile, you get the same result. For instance, to give one example. And it's the case of the changes in changes of Atta and Imbens, but it's not the case of this naive quantile diff in diff, which I will not recommend. And finally, and actually I will say a few words about that, if you do a decomposition, like in discrimination studies or Aka-Blinder decomposition, if you replace OLS with quantile regression coefficient, you don't get something that can be interpreted. But I will show you today something that can be interpreted. Okay, so this was actually just a short list of mistakes that you should try to avoid and that are very easy to do. But now I will start with the main topic of the lecture today, which is this unconditional quantile treatment effects. So I don't know if you have questions about this first part. Yes?
Can I ask a notation question? So when you were talking about the quantile operator not being linear and not having a law of aggregated quantiles, you used the notation q tau and then something inside the parentheses. And I wanted to clarify, when we have expectations, for example, those expectations are with respect to whatever random variables are on the inside of those parentheses. But with quantiles, the way that you wrote it there, should we take it to mean that it's the quantile function of whatever random variables inside the parentheses, or is it a particular quantile function that you then evaluate like different arguments, if that makes sense?
Yeah, okay. So actually, I was preparing the slide and was not sure what is best. It's pure notation. So it's, yeah, so here I think is that quite often I will have them something that is quite long here, and if I put a subscript, we don't see it well. So it's just for this reason that I have put tau as a subscript and then the random variable inside of the parentheses. So it's the only thing that you should read here. So this is a tau quantile of what is inside of the parentheses, and then we will consider both changing tau and considering different random variables here. Some papers are using one notation, some papers the other. I think I took the notation from your book. So I try. But yeah, you can find. So I was hoping he would use the same in his slides.
Yeah,
Okay.
It works well for your point about conditional iterative expectation.
Sorry, you?
It works well for the point about the iterative expectation for
Yeah.
implementations.
Yeah. No,
I think it's great notation, personally.
No. I did not take it like that. I mean, I really try to think about that. What is best? At the end, it's notation. Yes?
Can you go to the scatter plot?
Yes.
Yeah. So in the sense of OLS, this will be a problem of violation of homoscedasticity.
Yes.
But with quantile regression, this wouldn't be much of a concern.
No, but okay. So first, my point of view, it's not a problem for OLS. It's a problem maybe for some standard errors that do not allow for heteroscedasticity. OLS is fine. OLS, here, when all conditional quantiles are linear in X, then also the expected values linear in X, you get by integrating. And so here OLS is fine. And actually it's symmetric, so the median OLS would be exactly like the median regression. But the point is more that if you have independent errors which imply homoscedasticity, then quantile regression is not very interesting. It's more the point of these two slides is to say, if you are here, quantile regression is not interesting. If you are here, it's more interesting. So you don't want to have a model that imposes that. Now, if the data are like that, still to learn that they are like that, you need a method, and quantile regression may be a method to know about that. But if your model imposes that, and then if your model gives biased results, if you are not in this case, then it's a problem. Yes, okay. So to start with the unconditional quantile regression thing. Well, actually, it's the same vein as what I said before. Let's first consider the randomized treatment D. Okay, unconditionally randomized. So in principle, here we don't need the regressors. We have regressor x1 and x2, and we are interested in the effect of this randomized treatment D. If in such a case, because D is independent of x1 and x2, if you run the OLS separation of y only on D, of course always the intercept, but on y, of y and on D, or you run the regression of y on D and x1, which is the first set of regressor, or y on D, x1 and x2, asymptotically, the coefficient on D will converge to the same value in all cases. It's sort of trivial. if you think about the omitted variable bias formula, D and X are not correlated, so the omitted variable bias is 0. So in all cases, you get the same coefficient. If you think the intuition, oh, I forgot to see, the Frisch-Ford theorem, then when you regress D on X1 and X2, you get the same fitted values as if you don't regress D. And finally, if you think in terms of conditional average treatment effect, if you take the average of the conditional average treatment effect, then you get the unconditional average treatment effect. So actually, in these cases, you are estimating the same thing. So if you have unconditional or conditional effect, on average, you estimate the same thing with OLS. And like you already know with quantum relation, this does not apply. Now, why do you want to add control variables in OLS? You want to reduce the variance. Okay? So if these variables x1 and x2, they have an explanatory power on y, then adding these variables will reduce the standard errors. So you see very often applied papers showing first the regression on one, first showing the regression only on the treatment, and then adding variables to try to get shorter confidence intervals. And so the temptation, of course, is to do the same for quantile regression, but it does not work. It's not true. When you add control variables, even if they are independent of D, you are changing what you are estimating. So with quantile regression, you get conditional quantile treatment effects, and this coefficient depends on the set of control variables, even if they are independent of the variable of interest. So you cannot play the same game. Okay. Yes?
Are we thinking of well-specified linear?
Yes.
So, so how does it? That's kind of mind-boggling. So it's so
Okay.
it's
Wait. Well specified. Yeah. It's not about misspecification. Well, and
so the effect is independent and additive, but it changes if we add.
Yes, you can. I mean,
Yeah.
you may have. If you simulate data, not too pathological, there will be similar. But think about what you have. I mean, the paper Christian Zukov and others.
Yeah.
They have an omitted variable bias.
Yeah.
It's weighted by the density. So there is no reason that this omitted variable bias is 0. Yeah, let me check.
I guess I'm like stuck in the OLS situation because I'm thinking the effect is additive. Then if I take if it's d1 beta d plus x1 beta x1, and then I don't put in the x1, and that changes the beta d. Yeah, I guess we're so used to OLS intuition, but it is kind of shocking.
But yes. But okay, so it's actually when we think differently, it's not shocking at all.
Okay.
So
yeah, that's what I want to know.
so let's say one of these variables is, so you have experience and education.
Yeah.
Here, if you regress y and the intercept on d, and let's say you look at 0.9 quantile, top of the distribution, and y is the income, so it means you are the top 10% of the unconditional distribution. Now let's say that you take an individual that has a very high level of education, high level of experience, but given this characteristic, her wage is not so high. Maybe below the conditional median. But this person is still at the top of the unconditional distribution. So this person will contribute here to the 0.9 quantile treatment effect, but maybe here to the 0.4 quantile treatment effect. So when we change the conditioning set, we change the definition of the rank. And so we can get different results.
You change the spread of every d, so how that affects the slope on d.
Yeah.
Okay, I see.
Yes.
So when you were showing the two graphs, the heterogeneity and the elasticity, I mean, we could just
Okay, so you are saying maybe there is a variable that will capture heteroscedasticity and then.
Yeah, so, yes, basically.
Yeah.
It's an example.
Yeah, yeah.
That by adding H2, it's not correlated with the treatment, but if it reduces the heteroscedasticity at the at large values of X, you will change the value of the quantile.
Yeah. Probably you are right. Because that if it's not correlated with D, so but yeah, no, I think you're right. Yeah. No, you're right. Yeah. But what I was saying, the example I was saying is, if you take someone here below the median of the conditional distribution, but clearly above the median of the unconditional one. And so if you think as averaging these individual effects, so let's say that the treatment, then this person will contribute to below the median conditional quantile treatment effects and above the median unconditional quantile treatment effects. Okay. Yes.
So it's scary if it's possible that the treatment effect is found to be significant, say, with the X but not without the X. But here you're just saying that the quantiles change. Are you also saying that the significance of the effect will change?
Yes, I'm saying that. But if you take the integral over all quantiles, you get the average. And here we know by the OLS result that the average does not change. So it's just which quantile is significant and which quantile is not significant may change. But not if you have a uniform test, you have a functional inference. You may not be wrong. You will not be wrong in both cases. But if you consider one quantile, you may get different results, yes. Okay, so what can we do? And one solution is to look at these unconditional effects, but to use x's in the estimation. Okay. So now I want to generalize the previous result. I don't want to assume that the treatment is randomized, but if it is, it will still work, of course. So, but to have a better notation, I still consider binary treatment, and I introduce Neyman moving potential outcomes, y0, y1. In principle, it works also if the treatment is continuous. You have to do, we will see what you can do if you have a continuous variable of interest. Okay, so you have this potential, but it's simpler if you have this binary. You have this potential outcome, and now we are interested in the unconditional quantile treatment effect, which is the difference between the tau quantile of y1 and tau quantile of y0. We could do that for the treated, okay? So we could have the tau quantile treatment effect. Well, here, sorry for the notation. Should be a subscript, okay? Okay, so yeah, so here it's for the whole population. So the idea is, what would be the tau quantile if everyone is treated? What would be the tau quantile if nobody is treated? And we take the difference between the two as a way to summarize the effect on this unconditional distribution. But like I said, you could do that for the treated, you could do that for the control, you could do that for another population. We will see how it works. Now the observation rule, of course, you observe only one of y1, y0. If d is 0, you observe y0. If d is 1, you observe y1. And here we are assuming conditional independence assumption. It has many different names in the literature. And this assumption means, so what we are assuming is that given x, so here we need x, we need these control variables, so it's why we cannot just do a quantile regulation of y on a constant and d. We will need in some way to find a way to integrate x. So we are assuming that given x, d is independent of both potential outcomes. So this is fairly common assumption. Yeah, Pepe.
Just a quick question, and again, just because I haven't really seen these, but why is that a conditional QTE the quantity of interest? I mean,
Oh, okay.
it seems so weird. I mean, just like.
Okay.
So what policy problem do you have in mind when you use that as the object of interest?
Okay. First, I agree that you may be interested in that or not. social utility function, or I think social welfare function. Then with that, you can plug in your welfare function here and there, and then you can say if it's a treatment you want or you don't want. Like for instance, if you care about inequality, at the same time you can care about the level, and you have this social welfare function, you take that into account. You find a positive treatment effect, but maybe the variance is increasing, and the positive average treatment effect is maybe not enough to compensate for the increase in the variance. So you want to take that into account, and here you could plug in any. So it will not be, okay, well, it's not a quantitative treatment effect, it will be the difference between the utility function. Actually, the methods I will explain is you will get this CDF of y1, the CDF of y0, and then the results they work for any, I don't know, differentiable, so like differentiable functions of these two CDF. But a very prominent example is contact treatment effect. I think it's a nice way to summarize the effect. Now, I have a slide about that. Well, I think quantitative treatment effects, they are really nice when you assume ranking variance. And here, it probably makes no sense to assume ranking variance. While with conditional quantitative treatment effects, it's easier to assume ranking variance because you have this control variable that make people compare. So I agree that I'm not saying it's obvious we always care about that. But I think it's, okay, so it's, you have the distribution if everyone is treated, this will nobody is treated, so you can see on the, what is the effect on the aggregate distribution, and it's a way to summarize it. But yeah.
How would you say what you're saying that is there any case in which I would look at the say distribution of just y1 minus y0 and something about the quantiles?
Okay.
So I guess the annotation would be, would it be reasonable to look ever at the quantile tau of y1 minus y0, everything in parentheses
Yeah.
inside?
Okay, so if you have conditional ranking variance, then you can do that because the conditional quantitative treatment effect will be individual treatment effects, and then for each person you estimate the individual treatment effect, and then you can report the distribution of this individual treatment effect. Actually, at some point it was in the appendix of the paper containing the results here, and it was too long. If I remember correctly, it's a special case of the sorted effect in Victor and some other co-authors, I don't remember. But you can do that. You need ranking variance, conditional ranking variance.
Okay, awesome. Yeah. Just like I haven't seen this, and I was just like,
Yeah.
maybe I wanted to think about like,
Yeah. Actually, I was hesitating having the bullet point about the distribution of the individual effect. If I remember correctly, I did not put it on the slide, but you can do it. It's also a nice way to summarize the results, but you definitively need conditional ranking variance. Otherwise, yeah, I think it's not interpretable. While here you could say it's always the effect on the aggregate distribution. It's not the distribution of the effect, but it's the effect on the distribution.
have you guys ever, like, in this literature, is there ever, like, the possibility that the policymaker can make policy contingent on the value of tau? I mean, I don't know what
Yeah.
I'm thinking. I'm just thinking, I mean, these things arise now in the context of personalized treatment
Yeah.
system where you condition on X. So I'm just thinking, is there any instance in which maybe, there would be a reason for why the policymaker wants to think about implementing different policies for different tau levels or something like that?
Definitively. So here is one paper. I don't know what happened here. So last year in Proceeding of the National Academy of Sciences, it's actually a comment, it's 3 pages. They comment another paper. And it's exactly that point, is saying, because they are commenting a paper suggesting conformal inference for the individual treatment effect or personalized treatment effect. And they are saying, but actually you can use what you're observing, because for each person you observe either one or the other. We never observe both, here. Okay. So now we need this X because we need them to use this conditional independent assumption. And in particular, what that implies, what the assumption implies, is that the tau quantile of YD, so D can be 0 or 1, so control and tricky, we do that separately. The tau quantile of the potential outcome, which in principle is not observable, you can, by the conditional independence assumption, this is independent of D. So you can condition on D taking a particular value, 0 or 1, and then once you condition on that, YD is observed and it's equal to 1. Okay, so this is conditional independence assumption and this is observation rule. And so this is an identification result saying that the observed tau quantile of Y given X and D is equal to the tau quantile of YD given X. So this justifies estimating this one using this result with quantile regression in general, and if you add a parametric restriction, like a linear one for instance here, then you can estimate that with linear quantile regression. But here it's possibly non-linear, but the parametric assumption is linear, so you can estimate that with quantile regression. But this delta tau is not the unconditional quantile treatment effect I mentioned before, it's a conditional quantile treatment effect. So, and now I already said you don't have law of iterated quantile, so you cannot just take this conditional quantile of Y. You need to work with something else, and something else is a CDF. Okay? Because the CDF, cumulative distribution function, is an expected value. And so there is a law of iterated CDF, if you want. It's trivial application of law of iterated expectation. So with the conditional independence assumption, the result on the previous slide with quantiles, you can do it with CDF too. So the CDF, yeah, now I see I'm not very, yeah, I'm inverting, I see the notation. But anyway, okay, so the CDF of YD is observed is equal to CDF of Y given X and D. So, like I said, CDF is an expected value, so you have a law of iterated expectation. So the unconditional CDF is the expected value of the conditional CDF. So you have the CDF of Y given X, that you take the integral of the distribution of X, because we want the CDF of the whole population, so we just take the CDF of X for the whole population, and now using the result here that comes from the conditional independence assumption, we can replace the CDF of the potential with the CDF of the observed outcome, and this is something that we can observe and estimate. So, now we have a formula that links the conditional CDF and the unconditional CDF. We have quantile regression that gives us a conditional quantile function, but of course the conditional quantile function is the inverse of the conditional CDF, or the conditional CDF is the inverse of the conditional quantile function. So if you get the conditional quantile function with quantile regression, you invert it, you plug that in here. Here it's the observed covariate distribution, you take the integral, you get the unconditional CDF, you invert again, you get the unconditional quantile function. So there is this link where you start from the conditional quantile function, conditional CDF, unconditional CDF, unconditional quantile function. Okay? Sounds complicated, but you will see it's actually very simple. Yeah?
So heuristically, how do, because I would think of my quantile regression function, it's minimizing the objective I care about, like even just visually to give me a good linear approximation to the true quantile regression function. But now I'm wondering at the heuristic level, like how good does my estimated quantile regression function need to be so that things don't go crazy when I start, inverting, averaging, and then inverting back. I'm worried that like an approximation error would compound or something like that.
Okay, so you will like one slide. Well, instead of quantile regression, I say let's estimate that directly, and we call that distribution regression. We can do it.
Okay, yeah.
Then it will solve your point here.
Yeah.
Now, what I can say are at least two things. First, if you have a fully saturated model, then using quantile regression, by using quantile regression, you get the CDF in the cell. So it's a non-parametric model. And also another result is if X is continuous and use a non-parametric quantile regression or a non-parametric distribution regression, they have the same asymptotic distribution. Now the question is about misspecification, and I don't have a good response here. If I have the impression it's the same object, but I mean, like, if you approximate well the conditional quantile function, you'll approximate well the conditional distribution function.
Yeah.
But maybe it's wrong, I don't know.
Yeah.
Okay, so I know nothing about that.
So you just described two strategies. One is starting with quantile regression, going all the way to unconditional quantiles of the potential outcomes. The other one that you just responded to Gabe's question with was start from a conditional CDF and then go through the rest of the pipeline to get unconditional quantiles. I'm wondering if you were to go with the first option of doing quantile regression and then inverting the conditional quantile function to get the conditional CDF. Do we need the outcomes to be continuous?
Yes, it's a major difference between quantile regression and distribution regression. Quantile regression you need, okay, it's a little bit more complicated than that. Let me say a few words about that. First, in terms of model, if Y is not continuous, I think it's impossible to have a correctly specified model. I mean, except in pathological cases, because if you think about it, you have a line and you try to fit something that has mass points, it's impossible. Like some people have used this paper, Machado, Santos Silva, they use for count data, they use quantile regression and they add noise. I think there is no reason the conditional quantile will be linear or close to linear. It will be a step function actually. So in such a case, I think you want to use another method, and distribution regression works fine. Then I think quantiles are also interesting for discrete outcomes, but you don't want to impose linearity. So we have a paper where we are interested in these unconditional quantile treatment effects. Why is discrete or has mass points? We use distribution regression in the first step, and you can still report this quantile treatment effect. They still have sort of the same intuitive appeal, I think. But for inference, it's more complicated because it's no longer Adamo differentiable, so it's no longer asymptotically normally distributed. So it's tricky, but I would say you don't use quantile regression if there are mass points or if it's discrete outcome. Yes?
You might have also addressed this when responding to you, but I think I might have missed it. If it's the case that we would need continuous outcomes in quantile regression, but looking at the distribution regression, we don't require that. That difference makes me think that, okay, let me just use distributional regressions throughout. What might be reasons we would want to use quantile regressions over distributional alternatives?
think maybe in terms of interpretation, so first, even if we report that this is unconditional quantile treatment effect, we still can look at the intermediate step to try to understand how it works. And quantile regression is nice in terms of interpretation because in special case you have the classical linear regression model. So like you estimate for instance mean square regression, I have the impression we know quite well how to interpret that. Distribution regression, so it's a family of logit or probit, I find more tricky to interpret, and it does not easily, it's difficult to compare. This is first thing. Second thing, it's maybe not a very strong argument, but if you do simulations, and if it's not discrete, it's continuous, quantile regression tend to perform better. So I don't know really why, because non-parametrically it's the same, but different people have done simulations, and we have done simulations, and if you have a continuous outcome, we do better with quantile regression in terms of precision. So it could be a second reason. But I'm fine if, I'm not, I'm fine if you one or the other. Okay, other question? Okay, so here is the algorithm. I more or less said everything. So the first step is use quantum regression. And here, for instance, if you want to have a more flexible model, you do one quantum regression in the control population or control sample, one in the treated sample, so you get different coefficients here. Then you invert. Okay, so here is one issue, that the estimated conditional quantum function is not necessarily monotone. So when you estimate it, it may go up and down. Of course, asymptotically, it will be increasing. If it's not increasing asymptotically, it means the model is misspecified. So it's, if you want to invert something that is not necessarily monotone, it's not very nice, but you can use this formula here, which is the sample analog of a result you have in the population. So in the population, the quantum function is strictly increasing. So if you, this is one way to invert in the population, and in the sample, this will work. This formula will work even if it's not monotone. So what you are doing is just you estimate all tau. For all taus, you estimate the conditional quantum, and then basically what we do, we count the probability. What is the probability? So we want the CDF at one threshold, lowercase letter y, and here we count the probability or the proportion of quantiles such that the conditional quantile is below or equal to y. And so this, if you take in the population, you get exactly the CDF. A way to look at that is, it's the same if you use Chernouzukov, Fernandez-Valgalichon, or they have a paper about monotonization by rearrangement. It's the same. So I like this formula because here it's a sample analog of something that I play in the population. Yes?
Do we assume linearity of quantum functions?
So
Do we assume linearity of
here,
quantum functions?
yes, here I'm assuming it's a correctly specified model.
For every tau?
Yes. So, yeah. Inference is based on the bootstrap.
No, not about inference, just...
Yeah. No, for consistency, yes. Yeah.
It's because like in the Guillaume lecture we thought about what happened if we misspecify one quantum,
Yeah.
and here we assume infinite quantum, right?
Yes. Absolutely. So, yeah, there is a price to pay. We need to modelize the whole distribution. So, I mean, it's still more flexible than having like a conditional distribution. Now, of course, I see all models as approximation, so you want to be flexible, and but there is always a trade-off. Tomorrow we'll talk about inference after model selection. That could apply here. Yeah, that will apply here actually. So yeah, but definitively. Here the idea is really we can estimate the whole conditional distribution.
Okay,
Yes.
just to make sure, when you say that the problem with monotonicity is you fix x and the function as a function of tau is not monotonic.
Exactly.
That's
Yes.
what-
Yes. It's exactly.
So Guillaume mentioned in the morning, so is there a way of imposing that in the estimation explicitly that
Yes.
you want to get monotonicity for the particular tau that
Yes.
you're saying?
Yeah, there are different papers doing that. I think you should know better than me, but if you can impose it on the support of the axis we have, that they should not cross. Personally, for me, it's not a big deal. So in the sense that if it's misspecified, imposing monotonicity maybe can make it even worse. And if it's really, I mean, it should be nice. I mean, if it's so the swing is going up and down, I find it simpler to estimate quantile by quantile. It's faster, and then. But I see the point.
For the other case, when you do it jointly, I mean, how would you take into account the fact that you need information of the beta hat for different taus? So what becomes the objective function in that linear program? So it's not a check function anymore, right? Because that is only for one tau. I'm just having a hard time seeing exactly the structure of what's objective function and what's constraints. I can understand that in the support of the x's, you just
like doing rearrangement.
So number 2, okay. But then isn't number 4 guaranteed to be visible?
Yes, because, okay, when this one is, then this, by construction, this one is still increasing, or is monotone, this one.
Ah, yes, yes.
And then we integrate, so it's still monotone, and now we can invert without problem this one. Yeah, because, so I explain on this one now, here it's just taking the average, I mean, integrating our distribution of x. If you have a random sample from the population, it means taking the sample mean of the estimated conditional CDF, so it's at a given y, but here it's the average over all the observations you have in your sample. And if you want the effect for the treated, you will keep on your treated here, and so forth and so on. And then this one is monotone, so you can invert it to get the unconditional quantum. Okay, so but probably I'm slow. Okay.
Just one more thing.
Yeah, sure.
Kind of like open question, just like you know, like you guys are doing discussions. But say, if I just think about where the current literature is on estimation of average-driven effects on their own confoundings, right? Just the typical from y1, y0, the conditional on x, we have independence treatment sign. So say, like maybe 10 years ago or something, this literature would never estimate these conditional distributions of y to the next for average-driven effects. Inverse probability weighting would reweight the data. You would need to estimate propensity scores for doing that reweight when you could do this. So now times have changed, and now there's the double robustness business. So you can do this augmented inverse probability weighting. You estimate these conditional distributions, but you know, the big question is I need to get the influence for the correct influence function to put these things in. So is there a similar discussion in the quantum regression stuff? If you want to get an efficient estimator of this quantum treatment effect, what's the analogous of inverse probability weighting? What's the analogous of double robustness?
It's okay. So I want to say about inverse probability weighting, it's all the same. So and also it's older than you think. Like quantum treatment effect with inverse probability weighting is 3rd of April 2006, and this is semi-parametrically efficient. And if you do what you are doing here with non-parametric quantum regression, let's say here, it's also semi-parametrically efficient with the same semi-parametric efficiency bound. It's exactly parallel to the results we have for the average given effect. And actually, if you think in terms of CDF, it's all sort of trivial because you replace y with indicator function y less or equal to the threshold. So it's not surprising that it's all parallel. So
Well, then why do you say at the beginning that the double ML thing doesn't work? Because if everything is parallel, right? I mean, there's a version of implementing this double machine learning.
okay. So what I said was for quantum regression. For quantum regression, the naive double machine learning does not work because bias will be density weighted. So you need to do this double selection density weighted. But for the unconditional one, actually it's simpler.
Yeah,
And there is an earlier paper. So I will discuss these two things tomorrow. But for unconditional quantum effect, it's actually simple in terms of the double selection works. Because you can see that as doing things for the CDF, and the CDF is linear, so it's fine. But conditional quantum regression, it doesn't work like that.
Thank you.
So yeah, no, just really, so you don't need to do the reordering for Pierre's question, for the answer to your answer to Pierre's question to be, you don't have like a problem when it's near inversion, even if you have crossing and you don't do reordering because of the order in which you're summing.
This is actually doing the rearrangement.
This does the rearrangement.
Yeah. Because the thing is that, let's say you increase tau, it's going up, and then you increase tau, it's going down, then it's going up again. Here you will sort of count the number that are below, and it's the same as doing the rearrangement. Okay, so we need that here. Here we cannot simply invert that because it's not monotone. Okay, so it sounds very complicated, but actually, so this is the whole implementation in R, and it's for both the treated and the control. Okay? So actually, saying it's very simple, and I did that for 100,000 observations, 2 seconds. Okay, just one regressor, but it's completely feasible and not a problem at all. So what what I'm doing here, it's for the treated, so I keep only the treated. I do quantile regression. I do it on a grid. The next slide I explain a little bit, but here I estimate 100 quantile regression on a uniform grid between 0 and 1. If you have not too many observations, you can actually estimate really all quantile regressions. But if you have more than a few thousands, it's computationally becomes difficult. So here, 100 quantile regression, and I will explain on the next slide, which is this method, but this is very fast. Then here, I get the fitted values, so I take just the values of X for the whole population. It's only the treated here. Here's the whole population. Multiply with the coefficient, what I get is a matrix of fitted values, one row for each observation, one column for each quantile regression. And I do the same here for the control unit, same number of quantile regressions, and here again, fitted values for the whole population, so it's for the same, and here is the quantile regression coefficient coming from here. And then the unconditional quantile treatment effect is simply obtained by taking some quantiles, so here I wanted 5 unconditional quantiles, so tau 0.1, 25, 5, 75, 9, and here these quantiles of this matrix minus the quantile of that matrix. Why? Because I have a random sample, so each observation has the same value, and I have uniformly distributed quantiles, so each quantile regression has the same value. So you can treat that as a pseudo sample. It's a way to generate observation if everyone is treated, if nobody is treated. And like I said, so it's all what you need to do. Of course, we have written a package doing that in R and in Stata. But if you prefer to code like I prefer, you will see it's very simple. All these steps, actually here you have several steps together if you want. At the beginning I was doing all the steps, but then I saw that it's much simpler than it sounds. One slide about computation. Yes. Absolutely. It's my mind. I have two slides about that.
But so for this implementation in R, so this is linear is using LPSolve or whatever CAD solver R has for linear programs, or there.
Okay, so it's
or how's it?
It's Roger Kunka has implemented Barodal Roberts algorithm. Yeah. So that the next slide is about that. So in print, if you so the package contract is great. There are many methods. By default, you get the Roberts-Barodal algorithm, which is a specialization, but he knows much more than I do. A specialization of the simplex algorithm for quantile regression. It works well up to, I don't know, depending on the number of regressors, 5,000, 10,000, 20,000 observations. Then if you have more, like interior point methods, and if you have even more, you have pre-processing methods. Here, with this method, it's actually an algorithm that uses a pre-processing idea to estimate several quantile regressions. Because the intuition is, it's clear that if you have already estimated the 0.5 quantile regression, and you want to estimate the 0.51 quantile regression, they should be close together. And so actually you can do a one-step iteration, and we can prove that asymptotically it's the same. If you have small steps in tau, you can do one step. But still it's not numerically the same, so some people may think, well, what if you have a mass point, for instance, then the one-step estimator could work not so well. But there is something that is numerically equal, and the idea is the following. You have estimated the median, you know the 0.51 will be close. And to estimate quantile regression, the only thing you need to know is which observations are below, which observations are above the line. So if you estimate the median and you have observations that are clearly below, you know there will still be below the 0.51. Observations that are clearly above, you know there will also be above the 0.51 quantile regression. So you need only to keep observations relatively close to the line, and then you run a new quantile regression with one observation with a big weight for observation below, one observation big weight for observation above, and you keep only the observation close to the line. And you can actually check that the guesses were right. So you subsample, you estimate the quantile regression, then you take the big sample, but you keep only the observation close to the guess, and then you run a quantile regression with a much smaller sample size. Quite an old idea implemented in quantile. But here what we have done in a paper, we say, well, but let's do that for the quantile regression process. And actually, it's much faster. So even if you have big sample sizes, you start from 1, and then you go down and you go up, and you get the whole discretized quantile regression process. But what I did not say that if you have not too many observations, you can actually estimate all quantile regressions in R. With RQ, you put tau equal -1, and you get all of them. If you have no regressor, you have n observations, you know there are only n different quantiles. Even if in principle tau is continuous from 0 to 1, you cannot get more than n different values. With quantile regression, it's similar, but it's only of order n times log n. So it's a number of different quantile regressions. And you can actually get all of them by iterating a simplex like You do just one iteration.
On that, because I want to make sure I understand. So when you say the number of different quantile regressions, it's kind of like, is that the dimension of the grid of the taus? Like how many different values the beta tau function will take?
No.
Or what exactly are you
Okay.
different quantile?
Yeah, I should have started with that. In that, if you have not too many observations, you can actually estimate all of them, and the number is of order n times log n. But quickly, it's too much. This becomes too slow. So instead of doing that, we estimate on a grid. And in the previous example, I had 100 quantile
Grid of tau.
Yeah, exactly, a grid of tau. Yes. To prove the results, we need that the grid mesh slowly goes to 0. I mean, slowly.
Absolutely.
Yeah, so we need that for the.
N log n, that refers to the number of different points that you need to have in the grid.
No. It's a number of numerically different quantile regressions that exist. So if I give you 100 observations, probably you will get, I don't know, 150 different quantile regressions numerically. More you cannot, because actually it's a step function. That there are a range of taus that give numerically the same results.
That's what I'm saying. Like this is the different values that the beta tau function can take.
Exactly.
Right? So
Exactly. Yes. But we don't need that for the estimator to work. So for the estimator to work, we can estimate on a grid, and then asymptotically the grid should.
Let me clarify. So I think the reason why I was insisting on the grid is because in my head, if the number of different values that beta tau can take is of order n log n, that tells me that I need to have a grid that at least has at least these values if I want to recover the whole thing, right? Because if I put less values, I'm not going to be able to get all these jumps.
Yes.
Right?
But
So
yeah.
that's why in my head the number of different QRs, even though, so now I understand that it refers to the values of beta tau. It speaks directly to how fine of a grid I would need to have for the tau, right? Because if it's n log n and I put only log n, right, I would be missing. So I'd be kind of like estimating a function that has less jumps than what I know that theoretically you have. Does that make sense?
Yeah, but then the question is about need. I sort of disagree with the need in the sense that if you use a grid, you make some errors, but if they are of small enough order, you still get the results. And in practice, 100 actually is a lot. I mean, you do 50, 100, 200, and you do a few, you don't see the difference. In almost all cases, I know. So it's a question, it's like to show the result, we only need the grid mesh to go to 0 at the square root n. This for technically. And then in terms of practical implications, see, it matters so little that I really don't care. At the beginning, you care about that. Referees ask you to do with 20, 50, 200, 1000. 20 to 50, you see a little difference. 50, 100, you see nothing, and 100 to 1000,
because you're doing exterior point, but you're not walking all around the polytope. You're probably very close to the optimal solution. Because the problem is so similar when you just change the quantile. So you both reduce the size by doing the pre-processing, where you fix the size of some of the observations, effectively dropping them from the problem, but you can warm side. And we don't want to warm side exterior point method, so.
No, but I mean, if we have I mean, Jose is going to comment with it, but I'm just curious about this problem now that you do it iteratively, and you're
Yeah.
trying to get the whole process, right?
Yeah.
I agree that for one tau it's a linear program, and so it's a polynomial, right? But now you're pasting all these things, and even if you do it smart,
Yeah.
I mean, do we know anything about the complexity? Is this NP-hard or is this still polynomial? Because now you're pasting all this grid, and this grid has all these values that are n log n.
Yeah.
Like,
So I think
what's the theoretical complexity? Has someone written a paper about that?
I think like in practice, like I said, the number of tiles is not going up so fast, but either if you're doing the path or even just inverting test, so then you have to solve a bunch of quantile aberrations. So for inverting the aberration of your test, but then like it will be in practice quite a thing to stick with exterior point methods just because you can re-optimize, you can warm start. So you don't have to solve from scratch, especially for the path. The quantile process, yeah.
Interesting.
But I don't think there's specifically for quantile things like expected complexity, because that's the worst cases, but they're not very representative for algorithms in general.
But so here, you see that with a trick here, that even if you have a sample of 100,000, you see the first one, and after that, you work basically with 1,000 observations for each quantile regression. So it's why it becomes very fast. Yes. Someone else has a question. Okay, so asymptotic distribution. Yeah, I will give a sketch here of the asymptotic distribution. You have to look at this paper for formal results. I don't know how much you know. So I have one side about the functional delta method, because the trick here is we start from a first distribution, asymptotic distribution, which will be the quantile regression coefficient. And they will converge to some Gaussian processes that are well studied in the literature, quite old actually. Some result in the 90s and then also beginning of 2000s. And from there, we have the quantile regression coefficient, then we get the conditional quantile function, which is just a coefficient multiplied. It's a linear function, so it also converges to a Gaussian process. And then when you integrate, now when you invert, it's Hadamard differentiable, which means that we can use the functional delta method. Then when you integrate, it's Hadamard differentiable, we can use the functional delta method. When you invert again, we use again the functional delta method. And then we combine everything with a chain rule. So the formulas are quite complex, but to prove that it's square root inconsistent asymptotically normal is actually applying several times the same tool, which is not so complicated. And for the validity of the bootstrap is the same. Take the functional delta method for the bootstrap. Yeah, all the clocks are wrong, I think. So there is a functional delta method for the bootstrap, and then you can show like using these same tools that the bootstrap is working. So let's have quickly a look at the functional delta method. So yeah, maybe I not say we need the functional delta method because we are working with functions. So when we invert the conditional quantile function, it's not enough to use one. We need the whole function to invert and then to get a conditional distribution function. So let's call phi the functional of interest. For instance, when you go from the CDF to the quantile function, this is just the inverse function. And so now the question is, what is the asymptotic distribution of phi applied to an estimated function? So here we estimate the CDF and we apply the inverse, and we want to get. So we assume that the CDF is, we assume it can be proved. The CDF is asymptotically normally distributed. It will be square root n and some Gaussian process. And what we need is it's a way, it's a uniform differentiability, meaning that it must be differentiable uniformly in H. And then if you have these two conditions, by the functional delta method, you get something that looks like the delta method applied to one Mondamarian, one vector. And here you get that the asymptotic distribution of the phi function of the estimated f minus the phi function of the 2f converges to phi prime, which is the Adama derivative obtained here, applied to G, which is the asymptotic distribution of f. So let's see an example with the empirical quantal function. So we start from the CDF. The CDF is a sample mean. So the empirical CDF is a sample mean. Empirical quantal is not a sample mean. Empirical CDF is a sample mean. So we can apply the traditional central mean theorem to get that the empirical CDF at one threshold is asymptotically normally distributed, and it's a Bernoulli, it's a sample mean of a Bernoulli, so the variance is CDF 1 minus CDF. Okay. So now we want to go from the CDF to the quantal function, and so what we need is to generalize this result to the whole function. And this whole result, Donskerr, the original Donskerr paper, that shows that actually, if you look at this G hat function as a function of y, it will converge to a Gaussian process. Which means that if you take any fixed value of y, it's normally distributed. Any finite number of fixed values, they are jointly normally distributed. And in addition, the process is continuous. The sample paths are continuous. Okay, so what we have here, it means we have the first part. It's the part here. We have square root n estimated CDF, 2 CDF converges to some Gaussian process that we can completely characterize. Now we want the quantile to get the empirical quantal function, the distribution of the empirical quantal function. So this phi function is the inverse, you invert the CDF. And now here I give you the result, but intuitively, this is just the formula for the derivative of the inverse function. So the H function here, this is the H that you have here in the notation of Hadamard differentiability. And so what we have is, so minus y, because when the CDF gets larger, the quantal function gets lower, and inversely, so you get to minus. And then basically what you get here, it will be the asymptotic distribution of the quantal function evaluated at the tau quantal of interest that we divide by the density. So when you move, if you make, let's say you make a small error in the CDF, you want to know what is the effect on the quantal function. So if the CDF is a little bit too large, quantal function will be a little bit too low. Now by how much? Thing is, here the density enters, because if you have a high density, you make a small error in the CDF, it has only a small effect on the, you make an error on the CDF, it has a small effect on the quantal function. While if you are in a region with a low density, you make the error in the CDF, it has a big effect on the quantal function. And this 1 over the density evaluated at the quantal function is exactly the right, asymptotically, the right value with which you must multiply the error that you make in the CDF to transform it, to translate it into an error of the quantal, in the quantal function. Yes?
Isn't there a certain point that for the extreme quantiles you want to divide it by 0?
I'm cheating. In the sense that if you don't put assumptions on the tail's behavior, you have to cut somewhere. Yeah. Because it's no longer, then you have extreme value theory. You can do stuff. But in this paper, we did nothing, we cut, and then what we did is that where we cut, we can no longer get the unconditional one, which in principle could be very problematic if x explains a lot. Because if it explains a lot, let's say you have x and y, it explains a lot, then actually it may be that what you cut could affect the whole distribution, and then you would have to do things. But so we are cheating. So yeah, in the paper it's more formal where we define these tails, and also the thing is that for For the proof, you just need to say, well, at some point we cut, and no idea where. So it's, yeah. Yes?
This prime is the usual derivative, not the functional derivative.
It's a functional, it's a Hadamard derivative, yes. But yeah, it's not a proof. You have to look like van der Waart or other textbooks to get the formally. It's half a page or 1 page to get that formally. Here I try to give the intuition using the inverse of the derivative of the inverse function. And so what you get is asymptotically, for each fixed quantile, you get it's normally distributed. This is the G from the previous slide. So it means this is the asymptotic distribution of the CDF evaluated at this value of y. And then, so basically you get the same as for the height. Here it's this one, evaluated at the tau quantile. And then to translate into the quantile dimension, we divide by the density. And this converges to a Gaussian process, so it works also for any finite number of quantiles, but also the paths are continuous. Okay, so this is to show one application of functional delta method. Now, the sketch of the proof with the different steps. First, we know that the quantile coefficient, they converge to Gaussian processes. So, first paper showing that, Gutenbrunner and Jouret cover. I think they have some restrictive assumption, and Cherudukov and Anandval is less restrictive, but so we know that. So we have this result, it's not new. Then then we multiply basically with x, because we want the conditional quantile function, which is simply that multiplied with x. So it's a linear function of that, it also converges to a Gaussian process. Third step, we invert this conditional quantile function. If it's a continuous outcome, it's also Hadamard differentiable. Functional delta method, it means the estimated conditional CDF will also converge to a Gaussian process for the input system. Then, and this is a contribution of the paper I cited before, show that the counterfactual operator, what I call the counterfactual operator, is this integral here, where we plug in the estimated conditional CDF, and here it's also, we don't know the CDF of x, so it's the empirical CDF for x. We have a random sample from x, so we can plug it that here and there, and we show that this mapping is also Hadamard differentiable, so we can also apply the functional delta method. So this is the third step. No, it's fourth step, sorry. And finally, once you have the unconditional CDF, we invert again, this is Hadamard differentiable, again functional delta method. And so with a chain rule, we can keep all of them together and we get the asymptotic distribution. Okay, as you can imagine, because of all these steps, the asymptotic distribution is, it's a long formula where you have many things to estimate, like conditional densities, unconditional density, many different objects. Okay. And so instead of trying to estimate that analytically, we use resampling methods. And another thing is we want to make uniform inference. What is uniform inference is inference for the whole function. Okay? So because we do not only care about one quantile, but about the whole quantile function. So what we want confidence bands. This is one function with a minus, another function with a plus. And we want that the probability that the quantile treatment effect, that it could be for any quantile treatment effect, could be for another object, but we want the probability that the true value is inside of the band for all quantiles, where actually we cut the lower and the upper end. But in principle, for all quantiles, we want that the probability that the true one is in the band is equal to 1 minus alpha. So it's like a confidence interval, but for a function, and we call that a confidence band. And now, how do we get this confidence band? So first, we decide that, so this is a decision, that this band will be equal to the true one, plus minus some critical value that we will determine in the next bullet point, times the pointwise standard error. Yeah, the pointwise standard error, which is equal to, no, think I forgot to, should be divided, I guess. Sorry, it's typo. Should be divided. Okay, so now you see the issue is that we don't know this critical value. If you want to get pointwise confidence interval and you know it's asymptotically normal, then you put 1.96 and you have a 95% confidence interval. But the issue here is that we don't know. We know 1.96 would be good for one quantile, but probably not for several quantiles, and especially not for all of them. So we need something that is larger than 1.96, but we don't know by how much. And this critical value may be different from one case to the other. Because if the quantiles are strongly correlated, then actually something a little bit higher than 1.96 will do the job. But if they are like almost independent, if you move a little bit away, then you need a much larger because you are like in the case of multiple testing. And so the solution to that is to resample, to do the bootstrap and to mimic this, so we want to estimate this critical value, and the idea is this t should be chosen such that the probability that the estimated one, the true one, is in the confidence interval is equal to 1 minus alpha. And the way we do that is we use the bootstrap, and then with the bootstrap you can simulate the distribution, and then we choose the 0.1 minus alpha quantile of the simulated values as a critical value. Yes?
This is a very unfair question, but maybe you thought about that when you were doing this. Is there a way of trying to get uniform bounds directly on the bootstrap resamples? The bootstrap sample? So if I'm doing point-wise estimation, I can estimate the standard deviation on the bootstrap sample, but I can also get quantiles from the bootstrap resamples directly.
For that, we use bootstrap for that.
Yeah, I know.
And we use okay, so I don't understand the question.
So if I'm doing it point-wise, I can do the bootstrap, estimate the standard area of my bootstrap draws, and plug in here, and that's what we're doing in a uniform version because you take a sub.
Yeah.
But if I'm doing point-wise, I can also get my bootstrap draws, find the 0.5 and the 0.95 quantiles, and the region between that treat it as a 0.9 confidence interval. Is there a way of doing the latter if I'm interested in getting a uniform bounds?
Okay, I guess I'm still not understanding. So,
can I use directly quantiles of the bootstrap distribution instead of estimating the second moment in the bootstrap samples, even if I want uniform coverage?
for that we use the pointwise bootstrap, and then we use, it's like a percentile bootstrap for the test statistic if you want.
Okay. Yeah, right.
So,
but could I do a percentile bootstrap on paths?
Okay, you can do that on here it's called Smirnov idea. So we take the maximum deviation over the contact.
Yes, that I understand.
I was lost. Okay, so it's basically inverting the Kolmogorov-Smirnov test statistic.
Yeah.
You could do that for other test statistics, but then it's like percentile bootstrap for this one. And then the advantage of doing that is graphically, I will finish today on that. Graphically, if you have uniform bands, so here you have pointwise confidence interval and uniform bands. So it's a decision that you have taken to inflate the pointwise.
Yeah.
There are other ways to do that, but here we have done like that. And the advantage is, let's say you want to test an hypothesis that the contact treatment effect is 0 at all quantiles.
Yeah.
Here I have my uniform bands. It's enough if I find a single quantile, like this one, where 0 is not in the uniform band. So I can reject because the full function should be included, and here I have a value that is not included, so I can reject a null hypothesis that it's uniformly 0, for instance. Or you can test also the hypothesis that is constant. And here it's the same, okay, because here it's, but probably you should cut here because there is a mass point at 0. So here it's maybe more tricky to test an hypothesis that is equal to 0. Of course, if you have a specific null hypothesis in mind, you can try to do better. You can try, especially you can try to generate a bootstrap sample imposing the null hypothesis, you will get a more powerful test. Also, there is no reason that Coleman Smirnov is the best thing you can do. Gramophone misses, all those things. So you could think about doing all those things.
But then I'm wondering, there's no more brute force and effect. If magically all my paths, like 20 bootstraps showed up like one on top of the other, they never crossed, and I could pick and I had 100 of them, I could pick the fifth and the 95th one, and the two between them would be a uniformly valid 90% template band. But of course they're going to cross all over the place. I'm just wondering if there's a way of directly picking one.
No, I think the way is to define a test statistic and to do that.
Yeah.
But then we know that there is no test statistic that is uniformly more powerful. It will depend on the sort of deviation you want to have power against. And in principle, you could adapt that to the specific deviation you want to consider. You had a
I was wondering the same question in another context. I was curious. You'd think that if you have lots of paths, you can construct a set, directly from the paths that would contain 95% of them. And
Since we have infinite computational power to look for a small one.
Maybe I'm misunderstanding that. So what you want to do is say you take bootstrap draws out of let me do it in a Greek section.
Yeah.
Say I start with the point-wise 95% critical value for each one of the things, right? And I take a bunch of bootstrap draws and I count how many of the paths that I obtained from the bootstrap were containing the point-wise max. And then I see that it's not 95% of them. So I say, gee, I missed it.
Yeah.
So I make it a little bit bigger.
Yeah.
Now I do again the 95%, and I count, and now instead of 95, I have 98. No, then it's too much.
Yeah.
And then I start doing this bisecting. Right? So you're talking about that algorithm? Is
Yeah. So that's when I look. Yeah. Because I look crazy the paths.
But it's exactly that. But
That is equivalent to the sub T. I mean, Mikkel and I implemented that procedure with what we call like a Bayesian implementation of the sub T. But it's okay to I wrote the applied econometrics, journal of applied econometrics. But we had some sort of proof that they're first order equivalent. And we did it for Bayesians.
Yeah.
But I mean, for the bootstrap, I think it's the same.
Yeah.
OCEs.
Because in like in some cases you want to you have that your bootstrap going to be valid under weaker conditions if you directly get the quantiles of the bootstrap as opposed to estimating moments in the bootstrap samples. So that's why there's a procedure that works directly on the drawn bootstrap sample paths that seem like it would be attractive, but it seems not
This
obvious.
procedure, when we did it, we just did it for deep business that, see in the context that Bayesian guys, they wanted to have an exact joined confidence region that had exact Bayesian credibility. So we did it this way, we just grid search the critical value and that just gives you a region. But I mean, in this case, we get the same, no?
yeah, it's my impression. Actually, the way you explained was great. I should have explained like that. What you suggest, I'm pretty sure we can construct pathological cases such that it does not work. Because imagine that.
I'm not suggesting anything. I don't know how to do it.
Okay. Okay. My understanding was if you take. No, but okay, it does not work. No, I think it's the best way to. I mean, because if you take pointwise, it will not work because you don't know what is happening.
I mean, if the paths are really well behaved, I can find a tube that contains 95% of the realized paths.
Yeah, but
in the bootstrap. That's going to work, but that's going to be
but
terrible.
if the order is
Yeah.
because if the order is not, if the order is changing with tau,
This is
then
gonna
it
get
may
really
be
wild.
that they all go crazy at one point, and then it will not be valid.
And if they all go crazy at different points, then I'm going to have like the whole screen to be my region. So is there a way to, I don't know. Yeah, that's what I was thinking. I don't know how to do it.
So I think it's the closest to what you are suggesting.
Yeah.
I think I have to stop, right?
Yeah.
Okay.
I mean, you have a conclusion, but
Conclusion, yeah, I don't know. I don't know if some of you are doing applied work, something that is dangerous with quantum regression is you estimate many and then you peak after you have seen the result. And then it's a problem of multiple testing. That should be obvious, but when you see interpretation of results, sometimes it's not so obvious. So it's better if you use uniform bands, you don't have the issue, you are sure you can do that, you can pick quantiles, and you have the honest bands for the whole function. So if the object of interest is a function, you should have confidence band for the function. Okay? So it's the only conclusion I can invent now. But tomorrow I will keep.
thank you.
Thank you very much.
So we'll see you tomorrow, guys. Moi, j'ai jamais vu dans la preuve de dégager du net, ça doit être, pour moi, en fait, ça doit être un bon exercice au niveau de truth, parce que c'est Van der Vaart,
C'est ça, c'est ça.
Very nice. Okay, so I think we can Yeah, exactly. Eventually, if you're not just reading right away in a vacuum, but like going back to doing proof, you want to understand. Okay, great.
So I guess I have no time for panel data tomorrow, but because I still have 10 slides here, and then I will do the inference after model selection.
Yeah, and then I guess the things that go wrong at the beginning, like it wasn't. I can understand so like which problems have been resolved and which are like.
I think most of what I show is been resolved except measurement error. But the other, no, panel data is still very active. And then inference after model selection, you just have a few papers. Other than that, I mean, this is parametric, but if you don't impose a parametric restriction, it's... Oh, there is a... I think reverse econometric, Jan Zukov and some other people doing a sample selection for distribution regression. Slide d'avant.
You're not estimating the same thing if you put different.
Yeah, exactly. Yeah, exactly. No, but so I was not sure, and I've seen that the CDF, it's a contradiction between